Okay, very good morning, everyone. Welcome to the first session today of Module 8 of the HSMA program. And today we're going to be introducing the world of natural language processing. So we completed our machine learning module last week, having covered the sort of a couple of key areas around non-deep and deep learning algorithms and learning models, including the use of neural networks. And we'll talk a little bit about neural networks today, but nothing that you have to worry about putting into practice. We will cover a little bit more neural network stuff next week when you come onto the sentiment analysis, but you'll see it's pretty much the same as you've been used to, but there's slight wrinkles in how we deal with it when we're dealing with text data. But this morning we're going to be sort of introducing some of the core concepts of natural language processing, just to get you familiar with some of this stuff before we move on to this afternoon, talking about one of the great things that we can do in natural language processing, which is named entity recognition. So we'll talk a bit about that this morning as well, but you'll get a chance to have a practice using the fantastic Python package SpaCy to do that this afternoon. So just to say, natural language processing is a huge area, and we couldn't, much with with machine learning, we couldn't possibly cover everything in the HSMA course. So basically, much as with machine learning stuff, we are going to sort of introduce you to a few bits to get the ball rolling. But if you find that natural language processing is something that's potentially of interest for you, there is a whole world of it out there. And we very much focus the natural language processing training around some fairly simple but practical things that you can do. So there are far more complex and wondrous things out there that you may want to explore if you did a natural language processing project or had an element of natural language processing. But certainly from the next 3 sessions, you will hopefully get enough that you can go off and do some pretty simple but effective stuff with your free text data, and that's essentially what the tools that natural language processing gives you to be able to use all that free text data that hitherto has been very difficult to work with in an analytical way without some sort of manual intervention first. So hopefully the things that we show you will be useful and practical for some of the things that you deal with in your own organizations, and stuff that you can pretty quickly have a play with. You'll see that SpaCy, when we talk about it this afternoon, we'll talk a bit about how it works under the bonnet, so that you're aware of what that works. And a lot of what we did this morning, we'll be talking about some of the key concepts you'll need to understand. But actually, you'll see when we come on to Python code this afternoon, the Python code for SpaCy is incredibly easy. it's very easy to get really good stuff out of SpaCy. Okay, so let's talk about natural language processing first of all. What do we mean by natural language processing? It's commonly abbreviated to NLP. You'll often see it referred to as NLP. And it's basically focused around the way in which human language and computers interact. And there are kind of two key sides really to natural language processing. The first is where you're trying to get computers to understand natural language. So things like speech recognition. We've probably all got our home assistant devices, our things on our phone like Siri, and just glancing down to make sure my iPhone didn't wake up, and your Google Assistant, etc. We're all used to that kind of thing now. That's all natural language processing. Building AIs that can understand human interaction. That used to be less so now, but that used to be very much the measure of how can we, when will we know when we have created intelligence, true intelligence. And the test used to be the Turing test used to be that you would have to create a machine, a model that you could interact with, a human being could interact with, and they would be unable to tell that it is actually a machine that they are talking to. So actually natural language processing is featured quite heavily traditionally in AI methods. So there's that side of things, which is when I did my undergrad degree, that was what natural language processing was about. It was about trying to get computers to understand us when we talk to them. But there's another side to natural language processing, which is where we try to get computers to learn how we form our language, such that we can use them to automate the extraction of information from free text. And then that's what we're going to be focused on in this course. When we talk about natural language processing, we're not going to be delving into the world of speech recognition and stuff, as fascinating as it is, because that's going to be a bit less useful for you. It's also really hard, by the way, that kind of side of things. The developers behind the Amazon Echo and things like that, they have all confirmed this is really difficult stuff to do that. And actually it's for the kind of applications you'll need. We need the second bit is a bit more useful. It's about taking the free text data that you've got and being able to use usually AI-based methods in order to extract information automatically. So we talk about the automation of information extraction. What do we mean? Well, there's a number of things that we can do in terms of automating information extraction from free text. Three of the sort of most widely used things I've listed here, and I'll talk a little bit about. Two of them we are covering in this course. So the first is name density recognition. That's what we're going to look at predominantly today, and particularly this afternoon. That's what you're going to have a go at doing yourself. And name density recognition is where we try to automate the extraction of things we call named entities. These are things like people and places and organizations from unstructured or free text. And as well as extracting them, automatically categorizing them. So these are the people that I identified in the text. These are the organizations. These are the places that I identified, etc. And you'll see how that can be really useful to automate that information extraction. There's also what we're going to come on to next week, in next week's session, where we'll talk about sentiment analysis. And that's where we use AI-based techniques to try and identify whether a piece of free text, piece of unstructured text is positive or negative, or maybe even neutral in tone. We're trying to understand something about the tone of the author. And that can be really useful for a number of reasons that we'll talk a little bit more about this morning. And it can also work alongside something really interesting called sarcasm analysis, which turns out is incredibly hard, and we'll talk a bit about that later. There's also something called relation extraction, which we're not going to cover here. We may do a little masterclass on it in phase 2, because I've already got some materials I didn't use for HSMA 4 that I was going to do on relation extraction. Relation extraction is where you try to identify the relationships between entities in text. You say this is related to this, and you automate the extraction of those entities and their relationships into something called a relational tuple. So you basically say this person is the president of that. That's the relationship, and it can be quite useful for some of the stuff that you would look at. Okay, so let's think about a practical example of how natural language processing could help us. So let's imagine we've got a hospital, and that hospital has asked patients to fill out a survey about their experiences in the hospital. Pretty common thing that you probably all got some experience of. Now, in some cases, some of the surveys will contain very structured data. So it'll say, on a scale of 1 to 10, how did you feel about the level of care you received, etc., etc. But most surveys will contain some element of free text. And free text is very difficult to deal with because people can write anything. And so you can't, it makes the analysis of this much more difficult. And in fact, in practical terms, as you're probably aware, usually what happens is people then have to either be employed or people set aside to read through what people have written. And that's very time consuming and resource heavy. So actually, if we can have AI-based techniques that can automate that process for us and extract the key information from free text, can be really helpful. So imagine we've got some surveys. We could do some sentiment analysis on those surveys. We could identify whether the things people are writing are positive or negative or maybe even neutral in tone. We could identify the specific things that people are talking about positively or negatively or neutrally using named entity recognition. So we could try and identify, okay, well, people seem to be talking very positively about the level of care they received, or people that are on this ward seem to be talking very negatively. And we can also use relation extraction to try and identify the relationships between the adjectives and the things they describe to understand how people so how people describe their experience of various elements of a service. And we can also use something called aspect level sentiment analysis, which is what we will talk about next week. Let's start by talking about named entity recognition, though, which is going to be the focus of today, and particularly this afternoon when you have a go at this yourself. So what do we mean by a named entity? Well, a named entity is basically any real world object that can be denoted with a proper name. And the entity can either have physical existence. So Dan Chalk, I'm a named entity. Hopefully I have physical existence. The University of Exeter is a named entity. It's a thing that physically exists. But it could also have a more abstract existence. It may not have a physical existence. So something like discrete event simulation would be a named entity, but it doesn't, you can't touch discrete event simulation. It's a concept, but it is a named entity in that sense. Woodwork is an example of a named entity. And there are lots of ways in which we can categorize our named entities. And depending on the package you use, the way in which named entities are categorized can differ. We're going to be using SpaCy, which is by far the most widely used package now in natural language processing. It's become huge. So we're going to teach you that. And so these are the categories that SpaCy uses for named entity recognition. And you can also create your own categories as well. These are the default ones that come in, and you can see that there's quite a lot of different things. So we've got the category of person, which is for people, so entities that are people, including fictional people. NORP, which is for nationalities or religious or political groups. FAC, which is for facilities, things like buildings, airports, bridges, etc. They'd all be categorized as FAC. Org, which is for organizations like companies, institutions, etc. GPE, geopolitical entities, so things like countries, cities, counties. LOC, which is any location that isn't a GPE category location. So things like mountain ranges, which don't come under sort of country. It's not a country or city, but it is a location. Lakes, a good example of that as well. Products, so things like objects, vehicles, foods, etc. Things that aren't services. Events, so things like named storms, battles, wars, sporting events. works of art, titles of books, songs, films, law, which are named documents made into law, language, which is any named recognized language. These all probably make a bit of sense. Now, when we get down to these ones, you may not immediately think of these as named entities, but they are. And this can throw people off initially. So dates are actually named entities. So dates are basically any absolute or relative dates or periods. The date of the 27th of November would be a named entity, as would the last week of November would be a named entity. Similarly, times are named entities. So any time that is smaller than a day would come under the time category. Then we've got percent. They're named entities too. So percentages, anything that includes the percentage character is classified as a named entity under that category. Monetary values, including the unit of currency. Quantities, so things like weight or distance, any sort of measurements of something. Ordinal numbers, things like the numbers first, second, etc. They are named entities. And cardinals, which are basically numbers that don't fall under one of these types above. They are all named entities. And it can be a bit weird when you start doing named entity recognitions, because you don't often think of these things as named entities. And it may also be the case that you're not interested in these things. You might be, depending on what you're trying to do, but you might not. But the whole point of having these, not only extracting the named entities, but categorizing them, is so that you can say, look, I'm only interested in identifying the people that are being talked about in this text. And so you can ignore everything else if you want, and just grab out the named entities that have been recognized as people. Or you could just say, I'm not interested in any of these down here, we'll exclude those. You can do that as well. So that's part of the reason why things are categorized, so that you can, because you're probably not going to want to know all of the named entities and all the types of named entity for every piece of text that you look at. Okay, well, bang on time. So that makes a change. So let's have a practice of our understanding of named entities. You're going to have a very short little practice exercise now. You're going to go into your groups. You are going to study the following piece of text, and I want you to identify as a group all of the named entities in the text and categorize them according to the SpaCy categories that I've just shown you. If you feel that none of them apply, then you can create your own category and name it accordingly. That's entirely up to you. So here is the piece of text from which you are, as human beings, going to try and extract named entities. Yesterday, Derek went to Waitrose and purchased a loaf of bread and a pint of milk. Now, I will point out this was written a few years ago, so we can probably multiply the numbers by about 10 now. But at the time, it cost him a total of £1.30, which he thought was quite reasonable. When he was in France a few weeks ago, he felt that bread was priced a little too high. He's often wondered if he should learn a bit about bread making, but he'd have to learn the basics of cookery first. Poor Derek. Okay. Let's put you into your breakout rooms now, and you are going to try and extract the named entities from that piece of text. You will have 15 minutes. We'll come back at just after 10 o'clock. Hi everyone. Okay, so welcome back. Let me just share my screen. I'll go through a solution for this, and then I'll also, interestingly, I then tried this in SpaCy, which I never thought to do before, and SpaCy misses quite a few, I think. So I disagree slightly with SpaCy. This introduces you to quite an interesting problem with SpaCy, though, in that it won't recognize everything, because when we talk about it this afternoon, we talk about how it uses pre-trained models. You will use one of those, but that means you have to sometimes add to the training. There'll be things that it doesn't recognize, and there's interesting what it didn't pick up on this. So let me I will share my screen and show what I've come up with as being the named entities. I've picked up 13 of them. So where are we? Okay, so here I put forward that these are the 13 named entities in that text. Yesterday is a named entity. It's a date. It refers to a specific period of time that is greater than or equal to a day, specifically a day in this case. Derek is a person. That's a nice easy one. Waitrose is an organization. Loaf is a quantity, and bread is a product. Similarly, pint is a quantity, and milk is a product. And it cost him a total of £1.30, which is money. When he was in France, so France being a geopolitical entity, a few weeks ago is a date, because remember it relates to a very specific period of time. So a few weeks ago would count as a date. He felt that bread, again, a product, was priced a little too high. He's often wondered if he should learn a bit about bread making. Now, bread making and cookery, I would try to get the algorithm to classify those as a work of art, but you may want to have a separate category, so you might have had something a bit separate for those. But the important thing is when you come to use SpaCy for this kind of stuff, you kind of want to get to know how it classifies the things you're interested in, because you might find, okay, the things that it's picking up, it's actually categorizing them in this category. And if it's consistent in doing that, then you might just say, well, okay, that's the category I need to look for. Or you could set up your own category, and there's ways to do that as well in SpaCy. So a lot of it's getting the feel for how SpaCy will do it. Now I'm going to show you now. I will have a glimpse at I'm not going to talk through the SpaCy code, because we'll do that this afternoon. But I will switch over to my SpaCy screen. I just fed in. Let me just maximize that. So that's the code that you'll have a look at this afternoon. And I fed in that piece of text, and this is what it came up with as being the SpaCy's predictions, and they are predictions for what the named entities are. So it picked up yesterday as a date, Derek as a person, 130 as the money, France as being a geopolitical entity, a few weeks ago as being the date, and first as being an ordinal, which I think I missed. Yes, I did. Interestingly, I don't know whether we'd want to categorize that as an ordinal in the case, but it is technically an ordinal number. And again, remember, SpaCy doesn't have the answer. It's making predictions based on an AI algorithm, which we'll talk about later. But interestingly, some of the things it's missed, things like Waitrose, it hasn't picked up. That's an organization. We'll talk more about how it uses these pre-trained models later, and there's different pre-trained models that you can use, but it hasn't picked up Waitrose as being an organization. It's missed bread and milk, and bread making cookery have not featured. So in the particular prediction that we've got here, this is what's come up, but that might differ depending on which pre-trained model we use. But we'll talk a bit more about that when we get on to SpaCy properly later. So let's switch back to the slides. Let's talk a little bit now about noun phrases. So we know what named entities are now. How are we going to get a computer to automatically try and find them? That's the whole purpose of doing this. Essentially, with anything that we do in terms of our automation, we're essentially having to give certain rules to the computer that it can use to try and understand where it needs to find named entities, where it's likely to find named entities. Now, because named entities are based around things or nouns, to find a named entity, we need to look for things called noun phrases. So noun phrases are phrases that are either headed by a noun or an indefinite pronoun, we'll come back to that in a moment, or something that performs the same grammatical function as a noun. Okay, so to put it in a slightly simpler terms, because grammar is a little complex, particularly in the English language, a noun phrase includes a noun, such as a cat, and the modifiers which identify it. So my cat would be a noun phrase. John's cat would be a noun phrase. The cat with white stripes would be a noun phrase. The cat who ate all the tuna would be my cat, but also would be a noun phrase. So it's in each case, we've got a head noun, which is cat in this case. And I'll come back to John's cat in a moment. Follow along with all the things that modify that noun. So here we identify it's my cat. Here we identify it's John's cat. Here it's the cat we're talking about is the one with the white stripes. Here it's the one that's eaten all the tuna. That's the cat we're talking about. Okay. Let's just remind ourselves how fun grammar is as we trudge through this next section. So here's some examples of noun phrases where the noun phrases have been underlined. So these are the noun phrases, and the head noun is in bold. Okay, so the staff are very helpful, but the food was terrible contains two noun phrases. The first being the staff, and the second noun phrase, the food. Okay, so head noun, staff here, head noun, food here. A green-eyed Tom enviously watched Dan's amazing lecture also contains two noun phrases. The first being a green-eyed Tom. Which Tom is it? It's the green-eyed Tom that we're talking about. That's the noun phrase. Tom is the head noun, and it's the green-eyed, a green-eyed Tom. So that modifies Tom. And here, Dan's amazing lecture, the head noun is actually lecture. That's the thing that we're talking about, the lecture. And which lecture is it? Well, it's Dan's amazing one, although possibly that doesn't narrow it down. And then here, many universities, academics consume vast quantities of cake. We've actually got three noun phrases. We've got at many universities, universities being head noun. Which universities? Well, it's at many of them. Academics is a noun, but there's nothing modifying it, but it's still a noun phrase. So it's just a noun phrase consisting of the head noun and nothing else. Consume vast quantities of cake. So vast quantities of cake is another noun phrase. Cake is the head noun. That's the thing that semantically is holding the sentence. That's the focus of the sentence. And the thing that modifies the cake is the vast quantities of it. So that's how we describe the cake. So we've got universities here. We're talking about many of them, academics here, and vast quantities of cake here. We're talking about cake, but it's vast quantities of it. Okay, probably predicting where this is going. So, second exercise. What I want you to do is take these 6 sentences from the slides, and I want you to identify the noun phrases and the head noun in each noun phrase in these following sentences. So, sentence 1, 2 men walked into their local bar and thought their situation sounded like the start of a joke. Number 2, many students felt that Dan's tutorial was the best, but then again, people are often wrong. 3, most people tend to use Windows, but increasingly people are turning to Linux as it is a much better operating system. 4, suet can be used to make many different traditional dishes. 5, I think my black cat thinks I'm rather dull as he often yawns when I'm talking about my daily routine. And number 6, the above sentences show the random stream of rubbish that enters my head at any one time. Okay, so I'm going to give you just over 10 minutes. So we'll go to around 22 minutes past, maybe just before 25 past. Put you back into your groups. Pick up the noun phrases in each sentence and the head noun. Okay, I'll open up the groups. Hi everyone. Okay, so back from your grammar exercise. I'm sure you're loving this. We're going to do a bit more grammar in a minute as well, but don't worry, I'm going to as the day goes on, things will get a bit more fun, I promise you. So I'm just going to share the solution for this. So here are the the sentences along with the noun phrases which are underlined and the head noun for each noun phrase put into bold. So the first one, we've got 4 noun phrases. First one being 2 men. So men is playing the role of head noun there. 2 modifies that head noun. Their local bar. Bar is the head noun, and it's their local bar. So that's the modifier. Their situations, that's a noun phrase. Situation playing the role of head noun. And it's their situation that we're talking about. And here, this is a noun phrase, the start of a joke. Joke is the head noun there, and it's being modified by the start of a. So that we know what part of the joke we're talking about. Number 2, many students is a noun phrase. Students being the head noun. Dan's tutorial, so tutorial is the head noun, and it's Dan's tutorial. The best. Here, best is playing the role of a noun. It's playing the role of a tutorial. That's what it's referring to. It's shorthand for saying the best tutorial. So best is playing the role of the noun, and therefore that's the head noun, and the is the modifier. And we've got people being a noun phrase here. Then in this one, we've got quite a few. We've got most people, so most is modifying the head noun people. Windows and Linux are standalone noun phrases, as is people. This one here, operating system, is the head noun. A much better operating system is what modifies it. Depending on how you parse this, you might argue that system is actually the noun, a head noun, and because the operating, the fact it's an operating system describes the type of system it is, but for the purposes, I would suggest it's operating system as a noun. Then we've got suet can be used to make many different traditional dishes, suet being a self-contained noun phrase, and many different traditional dishes, so dishes being the head noun. And then this one here, so we've got quite a few instances of I being the noun phrase here, where it's the head noun, because of course I is playing the role of a noun, me, and therefore it counts as a noun phrase. So we've got, and remember, I'm is an abbreviated I am, so I is in here as well. Similarly with the pronoun he, that follows the same rule here. Which cat am I talking about? It's my black cat. And which routine am I talking about? It's my daily routine. And then in the last one, we've got two noun phrases, the above sentences, where sentences is playing the role of head noun, and then quite a large noun phrase here. So this one here, the head noun is rubbish. That's the thing that I'm talking about. It's the rubbish. And all of this modifies the rubbish. It's the random stream of rubbish. And it's not just the random stream of rubbish, it's the random stream of rubbish that enters my head at any one time. And there are quite a few nouns in there. You've got stream, head, as well as rubbish. But here, this is why we define a head noun. This is the thing that we're talking about. It's about the rubbish. We could remove everything else other than the word rubbish there, and that would still have the same semantic meaning. The above sentences show the rubbish. But all of this modifies it, describes that in some way. So it's the random stream of rubbish that defines it, and more of it's the random stream of rubbish that enters my head at any one time. So this is the noun phrase, and that's the head noun. And you can probably see already, so I'm getting you to do this manually. In natural language processing, you don't do this manually, but I'm getting you to see this is a bit of a pain to do this. So clearly methods to automate this need to rely on various methods that we're going to talk about today, and actually are really useful to be able to do this. But also because there are alternative possibilities. So Dan's tutorial is a good example. Here there are two competing nouns. Which one is the head noun? Now, as a human being, we can read that and say, okay, it's the tutorial that's actually the thing that's being talked about. That's the focus, and it's Dan's that describes that tutorial. But we've got to teach a machine to do this, and that's what we're going to talk a little bit about now. If I can share my screen. Okay, let's just keep reminding ourselves that grammar is fun. Perhaps write it down, stick it on your monitor, just as a reminder as we're going through this this initial trudge. So let's talk a little bit about definite noun phrases. So we've talked about noun phrases. What's a definite noun phrase? Well, a definite noun phrase is one where the head noun, the things that you've just been identifying, clearly refers to something specific, either something that's been previously mentioned or is known about, or something unique, or something that is being identified by the speaker. And so the head noun is prefaced by the definite article, the word the, unless the specificity of that noun is contained in the noun itself. So in the case of the number first, the ordinal number first, that's a noun, but it is a definite noun. It doesn't require the word the. Sometimes you'll you'll put that. But first, defines the specificity, because it is in it. The word itself defines it is the first thing. Okay. Now, the definite article might potentially be followed by various adjectives that describe the noun, and we'll come back to that in a moment. So here are some examples of definite noun phrases. I ran over to the dog. I sat next to the very fluffy cat. Those are both definite noun phrases, because the dog we are talking about here and the cat we are talking about here are very clearly specified. So here, I ran over to the dog. That sentence, if that was the only sentence in our text, wouldn't make sense, because, well, what dog? You've been definite, you've specified a dog as though I should know what that dog is. So presumably the prior text identifies the dog. Similarly here, I sat next to the very fluffy cat. Here we're specifying which cat it is. It's the one that's very fluffy. It's really fun, isn't it? This. Okay, indefinite noun phrases. We've got definite noun phrases. Now we've got indefinite noun phrases. So an indefinite noun phrase is one where the head noun refers to a singular noun where the reader or listener, depending on how you're consuming the text, does not know to which one we are referring. So the head noun in an indefinite noun phrase will be often prefaced by the indefinite article. So a definite noun phrase will have the definite article, the word the. Here we've got the indefinite article prefacing our head noun. So a or an, potentially again followed by some adjectives to describe that noun. There are also other complications. We are not going to go down that route. But let's just, for the simplicity, just assume that's what an indefinite noun phrase is. So here's some examples of some indefinite noun phrases. I ran over to a dog. I sat next to a very fluffy cat. We're not expecting the reader or listener to know the specific dog. We are saying I ran over to a dog. We haven't told you which dog yet. I sat next to a very fluffy cat. I haven't said which one. Now, why should you care about this other than, it's just so much fun? Well, it's because named entities are found in definite noun phrases. That's what gives them their named entity-like qualities. So if we're looking for named entities, we basically need to find definite noun phrases. That's where we'll find them. Okay, so we've said that named entities are indefinite noun phrases, right? And we also know that definite noun phrases will often have a head noun and it's prefaced by the definite article, the word the, unless it's something like a number, an ordinal number, which will convey the specificity without the word the. So in theory, it should be easy, shouldn't it, to identify definite noun phrases being the ones that have got the definite article in front and maybe have a separate rule for ordinal numbers. We can just look for most of it, just look for text that starts with the word the followed by noun. Surely, no, can't do that. That's completely wrong. Let's think about why we can't do that. Well, there's two core problems with this. Firstly, we don't just refer to nouns by themselves. We may, and indeed often, will use adjectives. We might say the cat, or we might say the fluffy cat, or we might say the very fluffy cat, and we'd need to pick up all of them. Okay, so the rule is a bit more complex than just saying look for the word the followed by a noun, or even look for the word the followed by an adjective followed by a noun, because you could have the very fluffy cat. That doesn't follow that rule. And there's lots of examples that fall into that trap. Second problem, we need to identify what is the head noun in a noun phrase. We touched on that a moment ago. There may be more than one contender, more than one noun in a potential noun phrase. The vicar, Brian, is an example of where you've got two nouns. Which one is the head noun? As human beings, we can see it's Brian. That's the focus. My cat, Bob, you've got Cat and Bob contending to be the head noun. So we, as well as trying to work out what the different patterns are, we also need to work out have a way in which we identify which is the head noun when we've got more than one noun in a noun phrase. So let's look at the first problem initially. And to do that, we're going to need to understand a little bit more about grammar. Yay! Something about parsing and about stuff called regular expressions. Okay, so let's start with more grammar, because why wouldn't you? Parts of speech we're going to talk about now, or POS, as it's very often known in natural language processing world. Parts of speech refer to the categories that we assign to words that describe their syntactic functions within text. Okay. This will transport you back, no doubt, to the things that we learned in school, most of which we've probably forgotten, other than a few of them. But in natural language processing, these things are actually really important. Now, in the English language, there are 9 parts of speech. As well as being incredibly fun, they are as follows. So we've got things called nouns, which we're probably all familiar with. We've certainly just had a go at looking at some nouns. So nouns describe the name of a person, a place, an idea, or a thing. Those are nouns. Pronouns are things that we can use in place of a noun. So things like me, he, she, it. These are all things that we can use instead of the noun. Rather than repeating the noun again, we can use a pronoun instead. Verbs, which are the doing words, they express actions or a state of being, are also verbs. We've got adjectives. So those are the things that describe things. So describing words for things are nouns. They modify nouns or pronouns. Remember, pronouns are things that are standing as a substitute for a noun. So they act as a noun, and therefore you can have adjectives that describe pronouns. Similarly, we've got adverbs, which are the same thing, but for modifying verbs. These are probably the ones that you're the most familiar with, and then these ones you're probably, oh yeah, I vaguely remember that kind of stuff. This is where it all gets a bit hazy now. But we've got these other things. So we've got determiners. So a determiner very specifically limits or determines a noun. So 2 dogs, the rabbit. So here, 2 is playing the role of a determiner. It specifies it limits the number of dogs to 2. The plays the role of a determiner here because it determines which rabbit we're talking about. And we've got prepositions. So prepositions will govern a noun or a pronoun. Remember, they are effectively the same thing, to express a relation with another word or element in the clause. So it's words like by and to and at. They're sort of linking bits within a clause that relate one thing to another. And then we've got conjunctions, which join words, phrases, or clauses together. So things like and, but, when. These are things where we say something and then I go on and say something else. But, or I also say this when I say that. So these are the sort of multiple clauses that are being linked together by these conjunction words. Things like and, but, when, that sort of stuff. And then we've got my favorite, which are interjections, which are specifically words that are used to express emotions. So it's words like hey, that's known as an interjection. Okay. Oi is a good one. So those are the 9 parts of speech, and every single word in the English language will fall into one of those categories. But of course, they will not fall into them not all words will fall into the same category, the same parts of speech every single time, because the same word can be used as a noun or maybe even as a verb, or you could have something that plays the role of a determiner but is also an interjection. So there's all sorts of complications that we will come on to. But the process of trying to label words according to their POS category is known as POS tagging. And this is something you'll see a lot in natural language processing. You're trying to identify which syntactic function, which syntactic role is this word playing in this piece of text, because that will differ depending on the context of that text. Ooh, this is, I mean, it's just so much fun, isn't it? Okay, right. You can have a go at this exercise, but I suggest you have a little break first. So go and stretch your legs for 10 minutes. We'll resume about 20 past. Let's say 20 past. Let's give ourselves a little bit of extra time. Because you've done a lot of grammar so far this morning. I promise you, things get more exciting. But we need you to understand these sort of core concepts first. So what you're going to do, you are going to POS tag this paragraph. Okay, so you are going to work out the syntactic role that each of these words is playing in this paragraph. The grey horse in the field was slowly eating some grass when she looked up and saw a bird fly onto the fence. The bird was then joined by 400 more birds. Wow, clearly the author had been watching too much Alfred Hitchcock. Indeed, I wrote this the day after I rewatched The Birds. So it just shows what influences my writing. Okay, so go and have a break for 10 minutes and then rejoin your groups. I'll open up breakout rooms now so you can do that whenever. And we'll come back, let's say at 20 past, to give you a chance to do this. Be careful, some of this looks easy. There are some little wrinkles in this particular paragraph that might trip you up a little bit. Okay, let's stop there. Go and stretch your legs and don't think about grammar for at least 10 minutes anyway. Okay, hi everyone, welcome back. Hope you managed to have a bit of a break there too, before going into more grammar. I promise you, it does get more fun, but you just have to we have to trudge through a little bit of the boring stuff initially just to get our heads around it. But things will improve. What you've probably found from that exercise is that well, two things. First of all, this is not fun to POS tag things manually. The good news is you don't have to. But the demonstration that I'm trying to make here is that actually POS tagging is not a trivial, as with a lot of these things in natural language processing, it's not a trivial problem. Because of course you've got the complication that a word does not have a single POS tag for every context that it's used in, and indeed the POS tags for the words that you've applied in this particular paragraph will potentially differ from the same word used in a different paragraph, different sentence. Let's have a look at the I'll bring up the solution, which I have double checked, so this is correct. There is a bit in here that's a bit weird, and I will explain that, and I'll also indicate how you might have POS tagged it differently. So let's start with the, which is a determiner. Determines it's going to determine this horse, the one we're talking about. Grey is an adjective which describes the noun of horse. In is a preposition. It's going to link where the horse is to in the field. So in is a preposition. The is a determiner. Field is a noun. Was is a verb, past tense of the state of being. Slowly is an adverb because it modifies eating, which is the verb. Some is a determiner because it determines the amount of this noun, which is grass. When, a conjunction because it's linking these two clauses together. She, pronoun, that's she is playing the role of the noun horse. Looked being a verb, and op being the adverb because it modifies the verb looked. And a conjunction because we're linking another clause in. Saw, which is a verb, a determiner. Bird, which is a noun. Fly, verb. Onto, which is an adverb because it modifies fly. The is a determiner. Fence is a noun. The determiner. Bird, noun. Was, verb. Then, which is an adverb, which modifies joined. When were they joined? They were then joined, so it modifies the verb in this case. By is a preposition. 400 is a determiner, as is more, because they determine the noun of birds. Wow, that's a nice easy one, interjection. Clearly is an adverb. The determiner, author, which is a noun, had verb, been verb, watching verb. I'll come back to too much. Let's skip on to the rest of it. Alfred Hitchcock, these are nouns. Too much. Now, this is an interesting one, and this is where people will often stumble, and I always have to remind myself of this every year. So you might have said that they are both adverbs because they are modifying. Oh, sorry, you might have said they are adjectives. Technically, the correct POS tagging for this in this context would be to have to as an adverb and much as an adjective. Now, here's the reason why, and I had to look this up when I originally did it, and I always have to remind myself of this as well. So you might have put them both as adverbs, sorry, not adjectives, because they're modifying the verb watching. But strictly speaking, that isn't correct. In fact, the word much in this sentence plays the role of an adjective because it is describing the noun Alfred Hitchcock. And because you've then got a word that is modifying an adjective, that then plays the role of an adverb. So to becomes an adverb and much is an adjective. That's the technically the correct solution for that. Don't worry if you didn't get that though, because it will trip you up. It is a bit weird, and this demonstrates perfectly why POS tagging is not a trivial task. It's actually quite difficult. Fortunately, the methods that you're going to see, including SpaCy, do this beautifully without any of your you needing to sort of manually intervene on any of this. So that's the good news. But hopefully this has given you a bit of an introduction to POS tagging and reminded you of some of that stuff that we all did years ago, and then most of it got forgotten. So let's move on and let's talk about parsing, which is what you've kind of been doing in these exercises so far. So parsing is a concept in natural language processing that you'll hear talked about a lot, and it basically means it's the process of breaking down some text, sentence it might be, into its component parts and describing the syntactic role of each of the components. So parsing would allow us to identify the noun phrases in some text. Parsing would allow us to identify the POS tags, the things you've just done in the last two exercises. And we can use things called regular expressions to help us in the parsing process. So a regular expression, which is sometimes known as a regex, is a sequence of characters that will define a search pattern. And they used to be used far more widely in old Google and other search engines. That was what was used. It was a regular expression based on. They'll still be used in some website search mechanisms, etc. Google and other big search engines use transformer-based architectures now, which we'll talk about this afternoon. But this is the way it used to be done, using regular expressions. And the way in which regular expression works is you define a pattern of text that you want to search for. So when we're parsing, when we're trying to break down our text into the syntactic roles of each part of it, we can use regular expressions to specify the rules for identifying certain syntactic structures in sentences. So here's some of the common syntactic patterns that some of the common regular expression nomenclature that we can use to look for certain text-based patterns. So these curly brackets here basically denote the start and end of a regular expression. We can use these little arrows here to say things like match a word with this POS tag. So VBD is a particular POS tag. It means a verb in the past tense. So find a verb in the past tense. I want a verb in the past tense. You can X question mark means match this thing optionally. So it might be there, but it might not, and that's okay. X plus means it has to be there. You have to have a sequence of at least one of these things. X wildcard means match a sequence of 0 or more. So you might have none, but you might have some. X bar Y means match X or Y. It could be this thing or that thing. The full stop means match any character. And the normal brackets here mean treat this as a group. So you could set up rules using regular expressions to look for certain syntactic structures. So you could have this regular expression here, which uses curly brackets and then the arrows and then NN. That regular expression will say find patterns of text that match a noun on its own. NN is a noun. Okay. Or you could have this regular expression, which says JJ question mark NN, which says match an optional adjective followed by a noun. Okay, so look for patterns that have a noun, but you might also have an adjective in front as well. So I want those things as well as those things that don't have an adjective in front of the noun. Anybody spot any problems with this approach?
It won't pick up any nuances in the text. So if there's anything that's slightly different, it'll miss it.
Yeah, so you've got to you've basically got to think of everything, because you have to essentially cover all the bases. That's a real problem with regular expressions. Any other thoughts?
It's not immediately parsable. Is a kind of, when you read it, you have to know what a regular expression is to know what it's searching for. So it's quite domain specific.
Yeah, I agree. I mean, regular expressions are horrible. I will say that they are not easily human readable. You have to know about regular expressions to understand them, and they are not nice things to deal with. So that is certainly a problem as well. Okay, so let's talk about some potential problems with the regular expression approach. First of all, it's a pain in the bottom, partly because of that, but also because, as was mentioned, there are huge numbers of things that we need to consider, huge potential combinations of patterns that we'd need to look at. And if we were using this to try and find noun phrases, remember, also definite noun phrases, which is where we will find our named entities. Turns out there's so many combinations of things that could be used, and we'll have to think of them all. And you'll find that some of the rules that you write will pick up things that they will pick up the definite noun phrases, and they'll also pick up stuff that isn't a definite noun phrase but happens to follow that pattern. It is a massive nightmare. In fact, there used to be, I don't have a link to it anymore, there used to be a little piece of code that you could use to try and build up rules that would identify definite noun phrases, and it would show you the accuracy. You'd have like a training text that you'd look at to come up with your regular expressions, and then it would try it out on some testing, and it'll give you the how good it was. And it was awful. I spent the best part of a day playing around with it, and I'd gradually be getting better, but then I'd put something in that would improve it on the training, and then it would find something else that wasn't an effort. It's an absolute nightmare, as you can probably start to imagine, even just thinking about the simple examples we had of the cat, the fluffy cat, the very fluffy cat. There's 3 different combinations potentially there, and that's without all of the other complications that you have, and that's just looking for definite noun phrases as well. So it's a massive pain. There's also possibly a more fundamental problem actually with the kind of stuff that we are likely going to want to use this for. So let's imagine that we're looking for named entities in patient notes made by paramedics at the scene of an incident. Now, that's something that you may want to use natural language processing for. Let's consider which of these possibilities we think is a more realistic representation of the paramedic notes. Firstly, first possibility, it was morning and a slight chill was in the air. I arrived to find that Mrs. Smith had clearly taken an unpleasant fall and was in need of help. Quickly and without a moment's thought, I rushed to her and asked if she was any pain. Or is the second example a bit more representative? Arrived AM, Mrs. Smith had fallen, rapid assistance given, asked if she was in pain. Now, clearly, that second example is a lot more representative because, let's be frank, it's very rare in those kind of situations, or even situations where we are asking patients to fill out surveys, that we're going to write in perfect grammar. But the problem is the regular expression approach assumes that we either write in perfect grammar, because the regular expressions will be looking for grammatical patterns, or that we are consistent in the way we write, so that somebody can predict the ways in which we might write. And that's neither of those things are true. We do not write in perfect grammar for this kind of stuff. We're not writing a novel. If we're trying to extract named entities from a novel, then we might have a bit more luck, or from a journal article, or from a news report. That would be a little easier. But even then, you'll have some complications. But when you're dealing with stuff like patient feedback, or people that have just written notes, or the GP's written some notes in it, they're not going to write in the way that you need for the regular expression system to work. So if regular expressions are not something that is going to be particularly useful for us for finding noun phrases, because it's too difficult for a start, and it's also too reliant on our text following consistent grammatical rules, that just isn't going to happen in a lot of cases. What do we do? Well, there is an alternative, and SpaCy is the alternative that we are going to put forward. And part of the reason it's become so popular in natural language processing is because it gets around a lot of these issues. And it basically, rather than uses regular expressions, it does use regular expressions for stuff, but the core of how SpaCy works is not using a regular expression pattern-based approach, but actually using AI-based methods. And we're going to talk more about those AI-based methods this afternoon. Specifically, it uses something called a transformer-based architecture. Transformers have transformed, pun intended, the field of natural language processing in particular. And we'll talk more about, they're very, very complicated, but I've got a nice, easy introduction to them this afternoon. You don't have to know all the ins and outs of how transformers work in order to use SpaCy. In fact, you could use it without understanding any of it. But as modelers, you should at least have a general appreciation of how this thing works. So we'll talk in general terms about how these things work. So SpaCy's very well regarded, very widely used now Python library in NLP, and the link to SpaCy is there. Hopefully you've all pip installed this, ready for this afternoon. But this afternoon, when we talk about SpaCy, we're going to look at how we can use SpaCy for a few things, but mainly for named entity recognition. But you'll also see that the parsing process that it uses its pre-trained models for, it does all the POS-tagging for you. It picks up what it calls noun chunks, which are noun phrases, and does all sorts of things in terms of monitoring dependencies between words. There's all sorts of things that does all in one go, and you can access any of that stuff instantly. It's really, really powerful. So we'll have a look at that this afternoon. That's the fun that's going to come. I'm also just want to mention though this morning, just talk a little bit about sentiment analysis, because next week we're going to look at sentiment analysis. As I just want to give you a bit of an intro to that here. So basically, sentiment analysis uses AI-based methods too, and it's trying to automatically identify the sentiment or tone of the author when they're writing that text, to identify, is this text positive or is it negative? Sometimes in sentiment analysis, we also look at whether it's neutral in tone. Personally, I think for a lot of the stuff that you will do, that's less useful. I think it's better to, and we'll talk more about aspect level sentiment analysis as a different way of saying what things are positive and what things are negative. So the way in which SpaCy works when it's trying to do something like named entity recognition, again, we'll talk more about this this afternoon, sorry, is that it uses AI to make a prediction. It predicts these things are named entities, and it uses AI to do that. It learns from large corpuses of text that are out there, and it learns, okay, I think this is a named entity. I think this is a noun. I think this is a determiner. And it learns that rather than using regular expressions. It learns these what's more, given the text that I can see, and given the context, which we'll talk more about this afternoon, what do I think this word is? And that's how it does it. Is a much more effective way than getting us to essentially write all the rules from scratch from the start, because we've already seen it's really hard. It's really hard to do that. So SpaCy uses AI for its named entity recognition and other stuff. The sentiment analysis is also an AI-based approach where we're trying to essentially here predict, given a piece of text, is it positive or negative or maybe even neutral? And so our inputs to that, our features, think of machine learning terminology, are the group of words that we've got and their POS tags and how they're co-located within a piece of text. Those are our features, and from that it then learns this particular bundle of words in this structured in this way is positive. This particular structure of words is negative in tone. So that's basically how it works. And you can have a go at doing this next week. So I'm just going to shut the door because my cat's going out. Okay, sorry. So we're going to go through this next week in detail, and you'll go through building a neural network. Yay! Don't worry, it's not too bad. You'll go through building a neural network next week to try and predict, get a machine to learn which pieces of text are positive and negative. But the basic process that you go through for doing that is we load in some raw text. We then clean up the data, much as we would for any machine learning problem. But obviously the cleanup for natural language processing is a little bit different because we're cleaning text. And we'll mention some of that stuff this afternoon, some of the things you want to do for that. This step is really important. This is unique to natural language processing, that we have to convert the clean word to numbers. Now, we mentioned last week in the machine learning that computers fundamentally have to deal with numbers, and neural networks, we have to feed in numbers. They work on numbers because they're doing weighted sums and passing outputs onto something else, and that's converting it to mathematical functions. They're dealing with numbers. They're multiplying things and adding things up. Now, obviously, we saw last week how we could do things in the synthetic data session, how we deal with stuff like, well, if we've got different categories, we can do things like one-hot encoding. So we put everything to a 0 apart from the category that it relates to, and we make that a 1. So that we're keeping everything as numbers. Now, obviously, what do you do when you're dealing with natural language processing? Because your data is all text, none of it is numbers. Well, you might have some numbers as text, but essentially it is all text data. So there are processes that we use to convert that text into numbers that mean something, and we'll talk a bit more about that. Once we've done that, we then convert it to the format usable by a neural network. Well, that's a tensor, so we put it into the tensor kind of shape. We then build the neural network, we train the neural network, and then we use that trained neural network to predict new data. So a lot of this process is the same as we saw for any machine learning, any neural network type project, where admittedly we skipped over the data pre-processing and said, you'll need to, if you do this for real, you're going to have to pre-process your data first, and here's some links that will show you how to do that. It's easy but boring and time consuming, unfortunately. But all of this you've seen, apart from this bit, which is the conversion bit, and that's quite important with natural language processing. We have to convert our text into numbers in a meaningful way. So what are some of the potential applications and challenges of sentiment analysis? Well, some of the potential applications, we could automatically classify service user survey data, put out surveys to our patients. We can automatically say who's talking positively, who's talking negatively, etc. For those of you who saw the HSMA 3 presentation event, if you haven't, go on YouTube and watch it. The one of the projects we had in HSMA 3 was from a chap named Mike Hill, who was from Avon and Somerset Constabulary, and created this fantastic dashboard thing that used a sentiment analysis algorithm in the background. Basically, it would scrape Twitter, it would grab all of the tweets to every police force in the country and automatically use sentiment analysis to classify them as positive and negative, and extract what people were talking about positively and negatively, and have a sort of league table of who was talking, who's being talked about most positively and who's being talked about most negatively. It's fantastic thing that he developed. So the stuff that you can do with that, and of course the great thing about using Twitter data is that it's all open, so anybody can use it. You can analyze reviews of stuff, so like movies and books, and we'll show you how we can use the Internet Movie Database as a good training mechanism for learning to pick up sentiment. Again, social media posts, so looking up, and this is part of the reason that Mike did his project, to try and identify other things that people are talking about negatively that we can sort of, you know, respond to in some way. You can also use it for automatically sort of going out there and looking for positive or negative references, things that people are talking about positively or negatively out there on the internet, on various websites about your organization. Now, potential challenge with sentiment analysis is the issue of sarcasm, and this is particularly a problem when you're dealing with social media text. People tend to be more sarcastic if they are tweeting something, for example. So I loved having to wait 5 hours to see a doctor. I was extremely impressed. I've never seen a restaurant with more dirt per square inch. Well done. You managed to ignore every request for help. Quite an achievement. These 3 sentences, as human beings, we would probably conclude that the author, in each case, was likely being sarcastic. Okay. But trying to teach a machine how to do that is actually quite difficult. And the reason is, this all contains positive language. I loved having to wait for 5 hours to see a doctor. Great. Positive review there. I was extremely impressed. Fantastic. I've never seen a restaurant that's managed to achieve this. Brilliant. Well done. Excellent. First class there. Well done. You managed to ignore every request for help. Quite an achievement. Achievement. Well done. These are all things that a sentiment analysis model will likely predict as being positive. Okay. But we as human beings can see, actually, I think they're being sarcastic. They're positive statements, but they're likely being sarcastic. Now, if we think about why we're identifying these things as sarcasm, well, why do you think we think those sentences are sarcastic?
Because we have preset expectations, and having to wait 5 hours is nothing that you would expect to do.
Yeah, absolutely. So it doesn't, there's a contradiction between what we're reading and what our expectations are for how somebody would feel about that. So I loved having to wait for 5 hours. Doesn't seem like something that people tend to love doing. I was extremely impressed. I've never seen a restaurant with more dirt per square inch. Well, we don't tend to think of people as being impressed by having a dirty restaurant. You managed to ignore every request for help. That, whilst that's an achievement of being flagged here, that's not something that we tend to think that people would tend to celebrate. So it plays into our expectations about this. It contradicts what we would expect the response to be for this kind of stuff. So there is a branch of natural language processing called sarcasm detection, which is a fascinating area, and it basically tries to use AI methods to identify when text is being sarcastic. So in the same way that you try to pick up something positive or negative, this tries to work out, are they being sarcastic or not? And of course, the most effective way to identify if a statement is sarcastic is, as we've just said, you compare it to a known truth. So if we know that people don't like waiting for services, then the statement, I loved having to wait 5 hours to see a doctor, is unlikely to be true, and therefore it may be sarcastic. Unfortunately, though, sarcasm is not easy. If we think about us as human beings, we very often fail to pick up when somebody is being sarcastic, particularly if it's in written text. If somebody writes an email and they're a little bit sarcastic, we can take it the wrong way. So it's very easy for us as humans to get it wrong. Now try and imagine we've got to teach a computer how to automatically pick up sarcasm. It's really, really difficult. And so it's a very interesting, but very, very difficult area, as it turns out. There's a nice little article here on this particular niche area of natural language processing and a little bit about why it's so difficult. They tend to use these transformer-based architectures, which again, I'll talk more about this afternoon to try and deal with it, but it is not trivial. It's a really difficult problem. So practically speaking, if you are doing some natural language processing on some sentiment analysis on some survey data or whatever, realistically, you're probably going to have to say, I'm going to assume that people are not being sarcastic. And you could check, you could take a sample, random sample, and have a look at the level of sarcasm. You'll likely find it's more of a problem, as I say, on things like social media. You will get, people will write sarcastic things in patient surveys, but it's less, I would say it's probably less of a problem than something on social media where people will tend to write things a bit more willingly. So it is definitely an issue. Interestingly, Mike, when he did his Twitter stuff, did some fantastic stuff looking at the emojis as clues to identify whether people were being sarcastic. So putting something and then having an emoji that contradicted the sentiment of what they've just written. Really interesting to look at that. But sometimes you see people tweet something and then they put a laughing face, and that contradicts what they've just said, or indicates they're joking about it or being sarcastic. So where the tone of the emoji, which is easy to identify because they're prefixed, contradicts the tone that you're identifying. Really interesting to look at sarcasm analysis using emojis in that way. But it's not easy. It's not an easy area to look at. So just be aware of that, and that it can trip you up. So perhaps you should design your patient surveys now with a warning: this may go through an AI and it may not be able to pick up if you're being sarcastic, so be careful. We might think, fantastic, we'll keep these weights up because people love it. There is also a further challenge with sentiment analysis as well, in terms of determining what the thing that they're talking about positively or negatively actually refers to, because they may be talking about more than one thing. And we'll talk about that more next week when we come on to the sentiment analysis session. Okay, so what I want you to do now is go into your group. So before lunch, we'll get you to do this for half an hour. We'll come back 10 minutes before lunch. And share some thoughts on this. Before we get into SpaCy this afternoon, get hands-on with the named entity recognition and generating word clouds, and having a look at DisplayCy, which is the display engine for SpaCy. The next 30 minutes, I want you to basically go into groups and have a chat about, let's just take stock about some potential application areas that you could think of in your own organizations for how natural language processing methods could be used. Are the things that you are thinking about that this stuff could be useful for, maybe even as project ideas for HSMA. So thinking about, are there potential ways in which we could use things like named entity recognition, sentiment analysis, all this kind of stuff? Are there potential ways in which this could be used? So have a chat about that. We'll bring everyone back, get a few thoughts before we break for lunch, and then as I say, this afternoon we will get into the fun stuff of actually doing this. The good news is the Python code is actually pretty straightforward for this stuff. Here's the link as well. I forgot I put this in here. If you want to look at the HSMA 3 event, the Mike Hill presentation that I was just talking about, you can click on that. If you jump to, what's the whole thing? If you've got the time, but if you just want to look at Mike Hill's 10-minute presentation, if you jump to 42 minutes and 40 seconds, Mike will talk you through. It really is. It's a beautiful demonstration of natural language processing as an HSMA project. Okay, so I'll put you into your groups now. We'll come back about 20 past, have a quick chat, and then we'll break for lunch before we get into this afternoon's fun with SpaCy. Okay, let's open up the rooms now. Hi everyone. Okay, so hopefully you've had a good chat there about some potential ideas. Heard a few interesting ones I was floating around. Anybody, just before we break for lunch, want to sort of share any ideas that they had for using some of this stuff? Silence.
I work in a mental health trust,
okay,
and we do outcome measures, so scores, so measuring a patient's condition at point A, measuring it again at point B, but they are scores on a scale.
Mm-hmm.
I wonder if you could combine that with like sentiment analysis of what the clinician is writing in progress notes. That might give you some more context, or it might mean the outcome measure isn't, because they're all quite controversial in one way or another, whether you could get more information about what's going on from what the clinician is actually writing in narrative form.
Yeah, that's an interesting idea. So one thing you could explore, and so something that is commonly done as well in so last year we had a project that did this, where sometimes you might want to do a kind of machine learning project and then think, well, actually we could try adding in some natural language processing to see, give us more features. Essentially, can we, if we then extract information from the natural language from the free text data, is by putting in that information as well, can we improve the kind of accuracy of our predictor? I was interested in one of the projects last year did that, and they I was trying to predict whether there was going to be an acute admission imminent, I think within the next 6 weeks, and they found just from preliminary sort of experimental work that adding in stuff from the GP notes actually helped to improve accuracy. So it indicated that there were clues in there that were useful as being predictors of it. So yeah, absolutely, you could do something like that. And in fact, you could just look at sentiment. You could also look at some of the kind of metadata about some of the text. So HSMA 3 project was trying to look at some of that, to look at not just what they're saying and the sort of tone of it, but also they noticed that if somebody was about to be admitted, they tended to get, this is looking at GP notes, they were tending to have a lot more written about them, and it was becoming more frequent. So sometimes just looking at some of the the frequency of the text and the frequency of the notes being entered and the amount of text being entered as well might, in comparison with the in conjunction with the what they're actually saying and the detected sentiment, could help there as well. Now, I think that could be an interesting area. You could look to see whether you can is this combination of words able to predict something about that. Any other thoughts people had?
We talked about to interpret radiology reports. A radiologist used free text to report imaging and the diagnosis that they find in the image. And the one example in a project we did, we found over 100 different ways to report pulmonary embolism in chest CTs. And actually that's quite tricky then, because there's huge variation in how individuals report. And my dog agrees that it could be better if we use NLP.
Yeah, no, I think that could be again a really interesting use, particularly where you've got that. It's kind of bringing some sort of order to the chaos. So yeah, I could see that being potentially really useful as well, and seeing where you could try and train it to automatically pick out the core information. And you could, as well as, so the principles that we use for sentiment analysis are essentially, when I give you this bunch of words together written in this way, that's positive, and when I give you this bunch of words written in this way, that's negative. In the same way as when I give you a passenger on the Titanic that is this age and this paid this much for their fare, etc., and the male, that they likely died, versus this passenger who had these features. It's the same principle that we're doing with natural language processing, with the sentiment analysis, that you're trying to say, given this combination of words used in this order, those are your features, and do we predict that's positive or negative? But of course, it doesn't have to be positive or negative. It could be, I predict this combination of words means this, as opposed to this. So yeah, that could be a really interesting way, I think.
We were looking a little bit at looking at ED data to grab kind of newly emerging trends in either a product, so a named entity product that kind of is causing harm. So I think a few months ago it was kind of Tide Pods. People were eating Tide Pods, and having that show up in a lot of ED data more frequently could be a useful thing for spreading information around new events and the adverse reactions to them.
Yeah, definitely. So keeping an eye on the sort of things that are sort of coming up and identifying those trends. I mean, that was part of the, again, going back to sort of Mike Hill's project, that was kind of part of what he was doing, was trying to, as well as, sort of ranking, 67% positive for this trust this month, or but actually to then pick out, well, what are people saying? What are the trending things that people are talking about? And so he obviously, for his constabulary and Avon, they had a lot of stuff around the kind of Bristol riots at the time, and there was, they could see that starting to trend in social media posts to them. So yeah, I think that could be really interesting to sort of monitor sort of trends over time as well.
We thought that is outside of the NHS, so to make the balance on all the projects. So that was our colleague Lauren. She was for the police force, and as part of sometimes looking at the proof is more and more frequent to have digital devices. They have to go through long chats, sometimes go for 1 year and 2 years, where you have to try to relate person A to person B in a certain context, and that be probably a good use to use a natural language to scroll those digital chats and whatever available.
Yeah, definitely. I mean, it's interesting you say that. So one of the HSMA 3 projects, another policing project, that they didn't end up getting around to the natural language processing stuff, but what they were hoping to do with that was to use modus operandi text data to try and identify the links, the relationships between offenders and their victims, and look to see whether they could use that information to try and sort of tailor their interventions. I mean, they just did some very, very preliminary stuff on that. They had to sort of prioritize them, but even then they were using some neural networks, and I think they were getting like 75% accuracy, which was pretty good. So it indicated there was something in there that they could do. So yeah, definitely stuff like that I think could be a really nice use of that. And I heard a few things come up in a lot of the discussions as well, that a lot of ethical dilemmas opening up with a lot of this stuff as well. So something particularly as we mentioned in the machine learning, anything around machine learning in particular, and natural language processing, kind of a subdomain of that, can lead to ethical dilemmas. So be careful in some of the stuff that you consider doing, unless of course you're doing Twitter, in which case you've got a free for all. But you still need to think about how you're going to use that and how you're going to affect people's lives as well. Okay, we will brilliant ideas I've heard there, and also floating around. So it'd be interesting to see what comes out, and also obviously as we start to show you how to do some of this stuff. So let's break for lunch now. So we'll resume at 1:30. And we'll look at using SpaCy. You'll get some hands-on time with SpaCy, and also generating some nice word clouds as well. So you get to practice some of this stuff. So as ever, you can remain on the call. That's not a problem. Just make sure you're muted and your camera's off. I will see you in an hour. Go and have lunch. Hello everyone, welcome back. So let's get on with this afternoon's session. So after the fun this morning of going through some grammar-based exercises, you'll be delighted to know that things get a bit more fun now. And hopefully this morning's given you a bit of an overview about some of the kind of potential of natural language processing, but also some of the core concepts to be familiar with. But this afternoon we're going to be focused on two things: named entity recognition, and I'm also going to show you a package, a really nice package called WordCloud, which generates word clouds. But for the named entity recognition stuff, we're gonna we obviously talked about what that means this morning. We explored it a little bit, but we're going to use the SpaCy package this afternoon to have a go at seeing if we can extract some named entities ourselves from some text in an automated manner. So SpaCy is the package. Hopefully you've all installed that okay. As I say, the link, there's lots of information on the SpaCy site that you can have a look at. There's lots of tutorials, explains quite a bit about how it works. But SpaCy is basically a free and open source library. We only teach those things for Python for natural language processing tasks, and it can do many things. But one of the thing we're going to be looking at today predominantly is it can do named entity recognition. Now, I mentioned this morning that the way it does this is using a transformer-based architecture. So it used to be, so you don't need to understand all the details of it. I'm going to talk you through so you get the gist of how it works, basically. To use it, you don't need to understand all the details. You just need to have a broad appreciation of what it's doing, and you'll find it's very, very user-friendly and very easy to use. But I'm going to talk to you about how it works, because it's quite important when you're trying to understand natural language processing. And actually, SpaCy has changed in the last few years how it works. So it used to use something called a convolutional neural network, which I'll talk a little bit more about in a minute. But since SpaCy upgraded to version 3 as of I think last year, it now uses a transformer based architecture, and transformers have completely revolutionized the world of natural language processing. And I'll explain that as well, what we mean by transformer based architecture. But before we do any of that, let's just so we're on the same page, we'll just go over a couple of the slides just to remind ourselves of the key bits from the neural network stuff that we did last week. So remember, we said neural networks are basically networks of neurons, originally called perceptrons, and they basically each do this very simple task. They take in some inputs into that neuron. Those inputs at the input layer represent the your data, your feature data, so the data in your various columns that you're trying to learn from, along with the bias, although you don't need to explicitly worry about that. And they get connected into the neuron, and each connection has an associated weight, and we multiply the input by the weight. So the neuron basically just says input times weight for all of the inputs, adds them all up, and then it spits it out the other side according to an activation function. And those activation functions, typically the most effective ones, are pretty straightforward. So ReLU is one of the most common ones, as we saw last week, and it just says if that number's positive, then keep it as it is. If it's negative, then just change it to a 0. So they perform a relatively simple function. And that's basically what the neuron is doing. But of course, we've got this back propagation element where we are checking to see how wrong we are in terms of the output that we get versus what we were expecting. And then a process that allows, an algorithm that allows us to adjust the weights to try and get closer to the correct answer. And essentially, these are our inputs. Which, as I say, the input layer would be our not quite our raw data, because we typically normalize the data for a neural network, so we put everything on the same scale between 0 and 1 usually, and we feed that in. Oh, excuse me. So we've got our inputs coming along, weights. We take the weighted sum in the neuron, and then we have this step function. Sorry, step function, activation function, which spits out the other side. Yeah, covered all that. So basically all a neural network is lots of neurons all put together in a network, and that network is made up of a number of layers. We've got an input layer, which is where we feed in the data. We've got an output layer, which is for a lot of the stuff you'll be doing is usually a single neuron, which will basically produce the number that you need, which is usually in a classification problem a kind of probability of it being a class 1 or not. And then everything in between is where the magic happens, and those are our hidden layers where all these numbers get magically sort of churned around, and weighted sums get calculated, and then they get passed on to the next layer, and then they do the same thing, and all of the weights are getting adjusted over time, so that magically this thing learns to, if I've got these inputs, I end up at the correct output. And we call it deep learning because of these this kind of layered structure. So that's a reminder of what a neural network is. Basically, it's basically a set of neurons that are all doing a fairly straightforward thing, but it's basically just taking in, each neuron's taking in inputs multiplied by a weight. It's adding those, doing a weighted sum on those inputs and weights, and then spitting out the other side according to an activation function. And that, if there's another layer, it'll then, those outputs from that layer will feed into the next layer as the inputs for that one. Now, in the previous versions of SpaCy, it used a particular type of neural network that you haven't looked at yet, called a convolutional neural network. Basically, a convolutional neural network is a type of neural network that was, well, still is actually to some extent, commonly used in both image processing and natural language processing. The best way to think about a convolutional neural network is a bit like a sliding window. So you're kind of looking at a bit of the data at a time, and then it's sliding back across. So if it's an image, you can imagine in having a sort of cardboard cutout, a little window, and you slide that window over the image gradually, and then each time you for each window you kind of feed that information through the network. So it's in the case of an image, it's trying to look for patterns of pixels within that window. With text analysis, it's basically the same principle, but it's looking at a group of words as your window, and it gradually shifts along. So maybe it's looking at the first 10 words, and then it'll look at the words 2 to 11, then it will look at the words 3 to 12, and then it's and so on and so on. So it's gradually shifting and looking at a bit of the text at a time, a certain sort of portion of that text, and only looks at those bits, that particular window at any one time. That's it. It learns through. We chuck those words through as numbers, and then we'll chuck those words through as numbers, and now we'll chuck those words through as numbers, etc. And that's how it learns in a convolutional neural network. They're really good for image processing, and they used to be the kind of gold standard for natural language processing as well. So for the kind of things that we're talking about, so for named entity recognition, for example, the way SpaCy we used to work is it would use a convolutional neural network, and essentially what it was trying to do is trying to predict whether a word or a group of words constituted a named entity, and it was making that prediction based on the words around it that it could see in that sliding window, along with their pulse tags. So as we talked about this morning, is it a noun, is it a pronoun, is it a verb, how far away those words are from the word it's trying to predict, all that kind of stuff. So it feeds that information in, and it's basically for each word predicting whether it's a named entity or not, and it's just trying to make a judgment, and it learns on vast corpuses of text. It goes out in the wild, and it just learns from text that it's seen out in the wild, these big data sets that it's trained on. So that's how it used to work, okay? And how you'll see a lot of natural language processing neural networks will use a convolutional neural network approach, because that was how it was done for a long time. However, it all changed in SpaCy 3. And now SpaCy uses what we call a transformer based structure. It uses these things called transformers, which, as I say, have completely revolutionized the way in which natural language processing is done. So I need to explain to you what transformers are. Now, transformers are not easy to understand. Okay, so I'm going to break this down and only tell you as much as you need to get the gist of it. You don't need to know the ins and outs of this for this. So bear with me, but I'm going to explain to you what transformers are. To explain what transformers are, I first need to talk about something called attention in natural language processing. So let's have a look at the following paragraph. This is a true story, by the way, and a glimpse into my life. So here we are. Here's the paragraph. My cat is called Prince, and he's very demanding. Every day he asks for treats at 11 o'clock. His 11s. You could set your watch by him. So accurate is he in asking for them on time. Sometimes when I'm teaching, as I am today, he has to wait for them, and he gives me a look that he's clearly not happy about this. Okay. Now I'm going to ask you some questions. So, you could set your watch by him, I said. Who could you set your watch by?
Prince.
Perfect. Excellent. Well done. He gives me a look that he's clearly not happy about this. What's he not happy about?
Waiting for his food and snacks.
Indeed, indeed. So accurate is he in asking for them on time, asking for what?
Snacks.
Yep. Perfect. Not particularly difficult questions, hopefully for us as human beings who are paying attention anyway. But this is demonstrating something. So as human beings, when we read something, or something's, we'll just stick with how we sort of read things for this. We relate the things we read back to stuff that we read earlier in the text. Okay, so let's have a look at this paragraph again. I said my cat's called Prince and he's very demanding. Blah 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 blah. Now further down here, sometimes when I'm teaching, he has to wait for them. Now we know as human beings, this he is my cat Prince. That's who it's referring to. Okay. Similarly, up here, I say that he asks for his treats, which are also termed as 11s. Down here, I said sometimes when I'm teaching, he has to wait for them. Now, as human beings, we can see, oh, right, yeah, the them that I'm referring to is his treats or his 11s. Okay. Similarly, here, this refers to having to wait for them. Okay. Now, this is known as the concept of attention. It's the fact that we can see when I'm looking at something down here, it relates, and we use a pronoun or something that it relates back. We're talking about something that we talked about earlier. Okay, I'm not having to say my cat is called Prince and my cat called Prince is very demanding. Every day my cat called Prince asks for a drink. We don't do that. We assume that the reader has some sort of attention span and is able to connect. The problem is the convolutional neural network approach that used to be used by SpaCy, and which is still fairly widely used, doesn't allow for that. Remember, it's looking at a bit of the text at a time. It's using this sliding window. So it's looking at a group of words. Therefore, because of that, the proximity of words to the thing that you're trying to classify becomes incredibly important. In fact, it becomes too important because it can't see anything beyond those words. So the problem is with the convolutional neural network down here, you might have a window that says sometimes when I'm teaching, he has to wait for them. The neural network has no idea that he refers to my cat Prince. So it's a real problem because it doesn't map the way in which we interpret and therefore write natural language. And because the way a convolutional neural network works means that so for image processing, it's actually really important because the proximity of, these pixels are next to these pixels are next to these, something like face recognition, for example, that's the kind of thing you want. But for something like natural language processing, actually, semantically, you may be jumping all over the place. So in a convolutional neural network, the proximity of words becomes too important. and therefore you can't identify long-range dependencies, words that relate back to things that you've read earlier in the text. So an alternative approach to try and capture this is to use what we call in natural language processing attention. So basically with attention, we can put portions of text against each other on different sides of a matrix. And then we can represent the relationships between each word and the word on the words on the corresponding side of the matrix. So we can use that stuff, and it has been used for things like translation. So we can put the text in English along one axis and the text in French along the other, and we can represent the relationships between these words in English and these words in French, and that can help us with translation. But there's also a nifty little feature, because those pieces of text don't have to be different. We can put the same portion of text on each axis. So exactly the same sentence in exactly the same language can go on both axes. And if we do that, then we can represent the way in which words within the same text relate to each other. And that's known as self-attention. Okay. It's so widely used now, though, that you'll just hear it referred to as attention, because that's typically what people mean. They mean it's technically a self-attention mechanism. It means that you are essentially, you've got this matrix that identifies the relationships between. So in the example I gave before about the paragraph about Prince, we could have the same text on both axes, and then wherever it says he and cat and all the other things that refer to Prince, we can identify it relates back to Prince. We can identify we're talking about the same thing. And that is transformative for how we deal with that long-range dependency issue in natural language processing. And it also emulates what we do as humans. Essentially, we've got a little matrix inside our head that we are, oh yeah, that he's talking about his cat Prince there. But there is another ingredient to this mix. Let's think about the following sentence. So John asked Mary if he could borrow her pen. Now, as human beings, it's likely we're going to assume that the thing that John wants to borrow from Mary is some sort of writing implement, not a female swan or an animal enclosure, even though we would use the same word, pen, for both of those situations. And what we're doing as humans is we're understanding the context. And in fact, sometimes we can get additional clues from additional text. So maybe the next bit is, this is because John was busy writing his memoirs. Although if maybe he's co-authoring it with a female swan. We don't know. But we're going to make an assumption here that he probably wants a writing implement. That tends to be something you borrow. You don't tend to borrow swans. Well, at least you don't here in Cornwall. Another two sentences to consider here as well. John was found eventually after hiding for some time from Mary, and John had got used to hiding his true feelings for Mary. Now, in both sentences, the word hiding is used, but in different contexts. So the first is describing John physically hiding from Mary, and in the second, it's referring to him concealing something intangible, his emotions. But the same word is being used, and it's got the same POS tag. They're both being used as verbs. But it's the context that helps us understand the difference. So the key message here is that in natural language, when we are talking or when we are writing or reading something that somebody's written, the same word can be used in different places in the same text, and even sometimes with the same POS tag, the same syntactic role in the text, but mean very different things. And as human beings, it's relatively easy for us to be able to pick up on those things, but a machine needs to be able to tell the difference. A machine, by default, is not going to know that John doesn't want to borrow a female swan, because it's the same word and they're both nouns. The thing that helps us to understand it is the context of the word, either in the sentence or the wider text, or in the absence of other information, where I said John wants to borrow Mary's pen. From our own experience, we understand context from the real world that's likely going to mean people tend to want to borrow a pen, a writing implement. So it's the context that helps us to understand how that word is being used, what that word actually represents. And as I say, clues within the text can help as well, and clues external to the text, so common phrases. It might be a commonly used phrase. All of this will help us to try and understand the context, how the particular piece of text should be interpreted. So basically, what a transformer does is it uses a kind of neural network based structure, but combines the concepts of attention and context. So it uses attention to try to understand the context of a word. So it's using, in other words, it's able to access those long-range dependencies by identifying this thing that's being talked about down here relates to that thing that was being talked about earlier. So it can do that. It's got that long-range dependency, that long-range vision. And it also encodes that context information alongside the word. So unlike a convolutional neural network, which is just looking at that sliding window, looking at a group of words at a time, and basing a lot around proximity, what words are around it, do I therefore think it's a named entity, for example? With a transformer-based architecture, we can pull that information from anywhere in the text to try and understand what the context of what's being written here is. And it turns out that is an incredibly powerful way to make far better predictions of what is a named entity, for example, because it's not just looking at a sliding window of 10 words or whatever it may be. It's looking at the whole thing, and it understands those long-range dependencies. And so this is what makes them so powerful for natural language processing, because long-range dependencies and understanding context are hugely important when we as human beings try to read and comprehend a piece of text. Now, there's much more to learn about transformers. I'm not going to even endeavor to go into the details. What I've just talked about will be enough for you to understand how SpaCy is working under the bonnet. It's basically understanding this concept of attention to get these long-range dependency information within the encoding, so that it can understand when something's being talked about down here, it refers to this thing that's being talked about up here, relates to it. It's a long-range dependency. If you do want to look into this a bit more, I use this as quite a nice basis for putting together the materials on transformers for this afternoon. It's quite a friendly introduction to it, and it'll also link out to some other stuff. But beware, they get complicated quite quickly, some of this stuff. So a lot of the materials out there on transformers are pretty heavy. This is a really nice introduction to it, so I'd recommend that. And hopefully now you understand the joke. What do we want? Natural language processing. When do we want it? Sorry, when do we want what? And that was the convolutional neural network approach. It's forgotten, doesn't know, has no idea what it refers to here. So you can now tell that joke to other bemused looking people who have absolutely no idea, and you can feel smug that you understand what that means now. Also, just flag up, it would be remiss of me to talk about transformers without talking about Sesame Street, because in natural language processing, apparently there's a general sort of obsession with naming everything after Sesame Street characters. So Bert and Elmo are two big things that came out in more recent years around natural language processing. Bert is a transformer model that basically revolutionized the way in which natural language processing is done. And Elmo revolutionized the way in which context is embedded, that encoding of context within that kind of structure. There's a nice little intro to both of those things at this link. And also you may have heard of OpenAI's GPT-2 and GPT-3 models. They're the big, powerful AI models. They are transformer-based models. The T stands for transformer. And so these are the models that can generate language that sounds like you're conversing with a human. If you want to read more about that, you can click on that link too. They are transformer-based architectures. Okay, that's how SpaCy works. Let's now get on to trying it out. So SpaCy, as I said, can do quite a lot. There's a lot of different stuff. In fact, this is taken from the SpaCy website, the link here, which lists all the different features that it can do. So it can do things on tokenization. I'll talk more about that this afternoon. POS-tagging, all that stuff you painfully had to do before lunch, it can do that automatically for you. Again, it's making predictions based on the learning that it gets from a transformer-based architecture. It can do dependency parsing, which is where you look at the syntactic dependencies between words, describing how they relate syntactically within a sentence. What's the for those of us mere mortals, that's stuff like what's the object of the sentence, the subject of the sentence, that kind of stuff. But there's a lot more to it, and your head will start hurting if you look into that. It is very interesting if you're into that, though. Lemmatization, which is getting the base form of a word. So the lemma was is be, for example. Segmenting individual sentences, linking entities, similarity is quite nice when you can look to see how similar pieces of text are to each other. You can imagine how that might be used for things like plagiarism, for example, and is used. Text classification, rule-based matching, training, serialization, all sorts of stuff. But we're going to focus on this one here. We are going to talk a bit about tokenization, although we're not going to use SpaCy's tokenization, just the inbuilt one for what we're doing this afternoon. So this is named entity recognition. So remember, that's labeling named real-world objects like persons, companies, or locations and other things that we looked at. Okay, so when we use SpaCy, there's typically 3 key steps that we do. The first is we load in a pre-trained model. So we take a model that's already been trained and we load it up so that we can use it on our text. That's going to be the thing that it's learned from this model. So that we're going to use that model to make predictions of our named entities, for example. Now that pre-trained model sometimes is referred to as a language in SpaCy. Okay, and we often load it into a variable called NLP. We can call it anything we like. We can call it blancmange if we like, but the convention, one of the conventions is to use NLP. So we load up the model and we store it in this variable here, which is now the pre-trained model or the language. Okay, so there's a model that's been pre-trained, and you've all downloaded that, one of those models, which we'll talk about more in a moment. Then once you've loaded it in, you apply that pre-trained model, the variable NLP, to some text to generate the various predictions. And SpaCy will do everything. It'll just do everything all at once. So it'll predict your named entities. It'll also do your POS tags, word dependencies. It'll do everything. And these predictions are stored in something called in SpaCy called a doc object. So it's a SpaCy structure. It's called a doc object. That doc object, we could name it whatever we like, but it's typically named either article or doc. Now I flagged that up because having learned SpaCy pre-SpaCy 3, and all the stuff focused on calling it an article. So that's how my training does it. I noticed the newer stuff uses the word doc. It doesn't matter, obviously you can call it whatever you like, but you may see doc used for the doc object, which is probably a better name for it, to be honest. But I tend to use article. It's both the same thing. It's a doc object. So you load in your pre-trained model, and that gets loaded into something that we typically call NLP. and then you apply that model, and all the predictions, SpaCy does its thing and makes all the predictions on it based on its prior training. And all of those predictions then get stored in this thing called a doc object, and that's how the thing we can access to get all of those predictions out, including our named entities. And we usually call that article or doc. So I'll be calling it article in these examples. And then once we've done that, we just explore the predictions that we can grab out of the doc object, and we can use DisplaCy, which is a great name. That's SpaCy's visualizer. The visualization engine for SpaCy, to visualize them, and it's a really nice little visualization engine. I'll show you how to use that as well. Okay, so hopefully you've all done this. Hopefully you've all pip installed SpaCy. I also asked you to do this command as well. What this is doing is downloading one of those pre-trained models. So the N-core web SM basically means the N is English, so it's an English language pre-trained model. SM stands for small. There's a medium one, MD, and a large, LG. They are increasingly large in file size. The large is really large, I think. I think it might be over a gigabyte. I'm not sure. But you'll get it's been trained on bigger corpuses of text, basically. It's a bigger model. And it's basically the core web just means it's been chucked out there in the wild on everything. So this is it's a good general model. Now, in reality, you'd probably, if you were doing this real, you'd compare performance looking at the small, the medium, and the large model at the very least, because you will likely you'll get different predictions possibly, because they've been trained on different amounts of text and different types of text. And there's also different types of pre-trained model out there. I'll talk more about that in a moment. But if you've done both of those things, you pip install SpaCy and then issued this command, this will download that pre-trained model. So now we don't have to train the model. It's already been out there and trained on text in the wild. Now, you've also been provided with a file called Trump article.txt. This is basically text from a New York Times news article from some years ago about the firing of an FBI agent. And what we're going to do is we're going to use SpaCy to extract the named entities from that news article, as well as their classifications, the predicted classifications. Remember, we talked this morning about the different classifications for named entities that SpaCy uses from that news story. So you'll have a chance to play around with this in the upcoming exercise, but I'll just watch along for now. So I'm going to open up, I'll open up both the text file and the Trump extract.py file, which is where the code is that will do the work. Let me switch over to Spider for that. So let's have a look. Bring up this is the text file that we're using. So this is just from a New York Times article from some years ago, and it's just copied and pasted into a text file. Okay, so that's all that is. It's just a news story. But we're going to try and automatically grab out the named entities from this news story using SpaCy. So here's the code that's going to do it. And even though I'm zoomed in, you can see, and even though there are quite a lot of comments on there, it's not a lot of code at all. It's actually very easy to do this. So first things we're going to do, we're going to import SpaCy. And we're also going to import the model that we're going to use, the pre-trained model. So in this case, that's the only one you've downloaded, which is the N-core WebSN model. So we'll import both of those things. Then remember, the first step is we need to load that pre-trained model into our, what we usually call a language. So we'll load this into the variable which we'll call NLP. And all we do to do that is call the load method on this model that we've imported. So in this case, N-core WebSM, and we just say .load, and that will load up the model, the SpaCy model, and it'll now be stored in NLP. So when we can now just use NLP, and NLP stores that pre-trained model, that stuff that's been out there and learned all of the particular nuances of the language, the English language in this case. and from which we can try and make some predictions. So we've loaded up our model. Then we're going to read in the document from which we want to try and extract the named entities. So in this case, I'm opening the Trump article .txt file. So you've seen this structure before. We can use the with command. Now this is a little bit different to what you saw before. Normally, I spent my time saying you don't tend to read in the entire. If you're reading a file like this, you don't tend to read in the contents all in one go. But for natural language processing, it's very often what you do. So here I'm using the read method of the file object, but I'm also using something called .strip. What this basically does is it reads in the whole file, that whole text file, as a single string. But the .strip tells it to get rid of any white space at the start and end. So it'll start with the first proper character and it'll end with the last proper character. So it'll read it all in as one single string of text. So that will now be stored in raw read. So it's read all of this into a string of text. Then what we're going to do is we're going to apply the pre-trained model, this NCore WebSM model that we've loaded in up here. We're going to apply that to that string that we've just read in from the text file to generate all of our predictions. Now, SpaCy, as I say, will do everything, including the named entity recognitions, but it will generate predictions of everything, and then we can just access whatever we want. And it'll store this as one of these doc objects, which, as I say, I call article, but you may see it referred to as a lowercase doc as well. And then what we're going to do then is I'm going to store the named entity categories. So for each named entity, it'll have an associated category, which will be like the geopolitical entity or person, those categories that you've seen. And these are stored. So remember, article is the doc object. That's where all of the predictions are going to be stored. Article.ents is where we find the named entities. So article.ents is how we get, because remember, it's not just named entities it's storing. It's predicted, it's done lots of different stuff. But article.ents will give us access to the named entities. And for each entity, we can grab .label underscore will get us the category for that named entity. So here I'm just using a simple list comprehension that says basically grab me for every called X, so for every entity in article.ents, for every named entity that you predicted, give me its label, its category. And that's x.label underscore will give us that. So we'll store that in a list called labels, and then I'm just going to print here. I'm just going to print each entity alongside its corresponding label. So let's do it. So actually, before we do that, let's just think about what we've done. We've done our imports. We've loaded our pre-trained model. We've read the file in that we want as a string. We've applied the pre-trained model to that string of text, and then we're just going to grab out the entities. That's it. That's all we've had to do. In fact, this last bit is just to print it so you can see it. So let me run this. Just very quickly read in that file, and then it'll apply the model to it. And here we go. So you can see it's picked out it's printed out a list of the named entities that it's predicted to be named entities alongside the category. So Congress, organization, FBI, organization, James B. Comey, person, Russia, geopolitical entity, Clinton, person, late September 2016, date. All the stuff that you were doing manually this morning, it's done that in seconds. Okay. And it's not just done this, it's done all of the POS tagging, etc. as well. But it's very quickly picked all that out. And in fact, if we look at the variable explorer, so I said that the raw read, that reads the entire file as a string. If I expand that, you can see that's exactly what it's done. So it's a single string, size 1, but it's just read in the entire thing. And then here's our list of labels here. The geopolitical entity, person, organization, person, geopolitical entity, etc. Okay. Really easy. Just pulled them all out. And actually, skimming through, looks like it's done all right. Looks like it's pretty good. We can obviously check, but it looks like it's pulled this out pretty decently. We haven't done any training. We're using a pre-trained model that's just been trained out there in the wild on things to look for to identify named entities using that transformer-based architecture that we talked about, so that it can see long-range dependencies in the text and learn from that. Okay, let's talk a little bit about SpaCy though. So SpaCy comes with this brilliant visualizer called SpaCy, which allows us to very easily see, rather than the print thing that I did there, which was just for sort of quickness, we can very easily see the outputs, the predictions that SpaCy has made about various aspects of our text, including named entities, which is the thing we're particularly interested in at the moment. So if we want to use SpaCy to display the named entity predictions, all we need is to add this line of code anytime after the pre-trained model has been applied to the text. Okay, so after it's done its thing, we can put this wherever we like. And all this says basically is it calls on SpaCy. So it says SpaCy.SpaCy.serve. This will basically spin up a server on your local machine. And you pass in two things. The first is the name of the doc object, which remember I called article. That's the thing that stores all your predictions, all the SpaCy predictions. And we pass in style equals, and then the particular thing we want to visualize. And on the SpaCy website, it lists the different combinations. So ENT, lowercase, basically gives us named entity predictions. So let's try it. Let's have a look at this one here, which is exactly the same. In fact, what I might do, let's take out this. Let's just comment out the print message to make it a little bit easier to see. Okay, so all this is the same as before. I've commented out the print, so I won't do that again. And I've just added this in, this SpaCy.SpaCy.serve, passed in the name of the doc object, article, and passed in, I said that I wanted to visualize the named entities. So if I run that, give it a second to do its thing. Now it'll say here using the ent visualizer, so it's doing the named entities, and it's serving it. And this is the web address. This is the address that, of the server that's just been spun up on my computer. Okay, so what I can do, I can just copy and paste that into a browser. Now, word of warning, because this tripped me up a few times. If you try and copy and paste here, right click and then click copy. Don't hit Control and C, because you'll remember if you're on Spider and you hit Control and C down here, it shuts down the code, which also shuts down your server. It took me longer than I would care to admit to realize what was going on when I was doing that. So just be warned. Okay, so I'm going to copy that, paste that, and there we go. Let me zoom in a bit so you can see that a bit easier. This is our text. This is SpaCy on the text that we've read in. And it's displaying our named entities within the text, and it's color-coded them and shown them for the different categories. So geopolitical entities here. We've got persons in this kind of purple here, light blue for the organizations, and we can see very clearly the predictions it's made. Okay. It's a really nice way to be able to visualize our the named entities that it picked up in a piece of text. You can see though, remember these are predictions, it's not the absolute answer. We see it's missed stuff. FBI hasn't been picked up there, even though it's picked up here. And again, it goes back, this demonstrates the concept of attention. It's not just using, oh, when I see the word FBI, that's a named entity. Because otherwise it would have done it here as well. It's not predicted this to be a named entity because of the structure of the text and the way it's learned. So it's not perfect. But obviously this is with one particular pre-trained model. Now, as well as doing named entities, we can also, I'll show you a little bit about how you can, actually, no, before I do that, just to mention, if you're doing this in Jupyter Lab or Jupyter Notebook, or indeed in Colab, the code that I've just shown you to display that will work, but it will throw up a warning as well. And the reason it will throw up a warning. We're going to the right bit. Sorry, I'm on the wrong side. Yeah, the reason it will throw up a warning is because that command that we've used, .serve, tells it to spin up a server. But if you're using Jupyter Lab or Colab, you're already on a server. So when you run Jupyter Lab, it spins up a little server on your machine, and you connect into that server on your machine. When you connect to Google Colab, it spins up a server on one of their machines, and you connect into that. So it'll work. That command will work, but it'll also throw up a warning saying you've already got a server running. So instead, you can just use this instead of the. So if you're using either of those, you can use this instead. So rather than serve, we use render. So we say spaCy.displacy.render, but then we pass in exactly the same stuff. So the name of the doc object and the style. And either way, let me just show you quickly that running in Jupyter Labs. This is exactly the same code as the spider example. I'll just run that. Oh, I forgot to take out the print message. I'll scroll down past the print message, and you'll see it'll appear below your cell in exactly the same way as it does the other one. Sorry, yes, there was a hand up.
Just so it's on the recording, I had to replace the 000 with localhost in the displacy server because otherwise the network blocked it.
Oh, really? Oh, okay. That might, yeah. So you might run into issues with some of your IT equipment. So you might be, if you can use Jupyter Lab, you might be better off doing this in Jupyter Lab because you're just using the server that's already spun up then. So if you do, people may run into it. You may not even, in some cases, be able to access it at all. Just be warned of that. So yeah, a good point. It is unfortunately, it's we'll come across this in a couple of weeks' time when we use Mesa for agent-based simulation. It does the same thing. It spins up a server for the visualization, and that might sometimes cause issues. So yeah, thank you. Just to be aware of that. Okay, so that's a really nice, easy way in which we can automatically visualize those predictions. But as I say, it doesn't just do named entity predictions. There's all sorts of stuff. So we can get it to display dependencies. So if I switch back to Spider, I'll just comment that one out. And I'll switch this one on. So exactly the same amount of code, except the style this time is dep. So if I run that, oh no, I need to close that down first. And then run it again. And now if I go back to my web page, if I refresh it, there we go. So you can see now we've got a different visualization, and this is actually displayed the syntactic dependencies within the text. So this is stuff like subjects of sentences, objects of sentences, how modifiers link together, the determiner particular. It's that kind of stuff, which can get quite, as you can see, quite complicated. In fact, if I zoom out, you can see it's not a very nice way to visualize this. In fact, there's a better way of doing it. And if you did want to look at the dependencies, this is a nicer way to do it. This third example here, where we, rather than pass in the entire the entire string of text in one go. Instead, we can take the list of sentences. So here, I store each individual sentence, and I cast as a list article.sense. Remember, article's the doc object that stores the predictions. I can grab out the individual sentences from that, because part of the thing that SpaCy does is it does tokenization and breaks the text down. So I can automatically grab out the sentences by using this, and then I can pass in that list of sentences instead. So if I do that, shut that down first, run that again, and you'll see it'll be a much nicer visualization. So again, you won't be able to see this very well because I have to zoom out so I can show you, but on your own computers you'll be able to see this a bit easier. It's actually done it sentence by sentence now, so it becomes a bit easier to go in and have a look at the particular structure of a sentence. Oh, that's that bit. And there's lots of other visualizations you can do as well. If you click on that link, it shows you various things that you can do in terms of the visualizations based on various SpaCy predictions. Okay, time for you to have a bit of a play around with this. So what we're going to do, I want you to spend the next sort of 20 minutes. So we'll resume at let's say 5 to 3. Let's give you a little bit of time to play with this and also have a stretch of the legs as well. So I want you basically just have a play around with SpaCy and what I've shown you. So run the code that I've just run, the trumpextract.py, look at the predicted named entities and their categorizations, have a good look through that. Run the code trumpextract2, which is the one that includes the DisplayCy stuff. Have a look at that too. And then try running the code on some text of your own. So all you need to do is just put it in a text file in the same directory, and then load up that file name instead, and have a look, see what it does. Maybe have a little explore of some of the other visualizations that you can do with SpaCy using the link here as well. So have a look, just get used to using SpaCy and how it works. Just have a bit of a play around for the next sort of 25 minutes or so. Okay, so we'll come back about sort of 10 to 5 to, something like that. I'll put you into your groups now, and I will see you shortly. Hi everyone. Okay, I thought I'd bring us back because I think you all had a bit of a play around with it there. So a couple of things that sort of came up as I was floating around the room. So and I'll talk a bit more about this in a moment, is there are if you went on and tried different sort of texts other than the Trump article, you might have found sometimes it picked up on things in the wrong way, it classified them in the wrong way, or maybe it missed certain things. So remember, you're using a pre-trained model, and you're using the small version of the model, which might work fine, but you might find that you need a larger version of the model. So remember, there are medium and large versions of the model too. You can actually, let me bring up the slides because we're going to talk about this anyway, but I will, you'll see I've put in, oh, and Mike's just added, fantastic. So there are a couple of other alternatives to SpaCy that are built on SpaCy. They work in the same way, but they're actually dedicated to particular areas. So SciSpaCy is a big one that's used, which I've put a link to in the Module 8 channel, where you've got very technical biomedical data in your text, that can be quite useful. So one of the groups in HSMA 3 used that when they were looking at GP patient notes, and they found it was a lot more effective at picking up some stuff on that. So it works. You have to install that separately to SpaCy, but it works in exactly the same way, and it's got its own set of models. And in fact, if you look at the links, you can see the different models that it has, and there's like some models where it has its own entity types, such as, you know, DNA, cell types, etc., which are more relevant to sort of heavy biomedical text, for example. Mike's also posted up about MedSpaCy as well, which is for sort of another good one for clinical natural language processing tasks. So you can check both of those out. They might be, depending on what you're trying to do, it might be a better fit. So obviously the stuff that we're using, the kind of standard SpaCy models, are trained on general text, so general articles on the internet, web page stuff. That's the kind of information it's trained on. But you might find something, depending on what you're doing, something a bit more domain specific might help you. It depends. Obviously, you know, if you're looking at GP notes, you probably need something a bit different to if you're looking at patient survey results, which the patients probably aren't going to talk in complex biomedical terms, so that would probably be overkill for that. But if you're looking at, you know, notes from a consultant or something that they put on, that might be really helpful. Or if you're looking at, you know, sort of journal articles, then that could be medical journal articles, that could be really useful too. So I'll talk a little bit about that just before we move on, because I think that's quite useful. So those are the links that have been popped up. Where are we? There we are. So hopefully you've seen that it's not bad as a starting point. And remember, you're only using the small model. You should get much better performance with the medium and large models as well. Although bear in mind they are, you can end up with the sort of the old overfit underfit problem. You can end up with it's picking up too much, or it's it's getting a bit too sensitive to stuff. So there's a bit of a play around with different things and see what works. But whatever you do, they won't recognize everything. Okay. There will be certain words and syntactic patterns that it hasn't seen before, and which make the learning, it's kind of got a learning black hole there, so it's making its best guess. I think one of the groups had a situation where they put in some story about the World Cup, and Wales had come up as a geopolitical entity, but also as an organization and also as a product. So it was really struggling with the country of Wales for some reason. But you will find little wrinkles like that. There's different things you can do. So one, as I say, is to choose a model that is a better fit or a larger model. This link here takes you to all the SpaCy models, as well as the English language ones. There's ones for loads of languages that you can use as well, and they're all the kind of SpaCy hosted ones. But as I say, the core models are trained on general text, so things like blogs and articles and comments and things like that. But there will also be other stuff. So there's the stuff that's been trained on medical papers, and medical journal stuff, the stuff that Mike and I have sort of linked to. There's stuff that's been trained specifically on Twitter, which will be useful if you're doing any Twitter-based stuff. So it might be a case that you need to find a better fit for your particular domain. Frankly, you can just Google SpaCy models and you'll find loads of them. There are a lot of them out there. The other thing you can do is something known as transfer learning. I don't know if I meant, no, I don't. I took that bit out. So what you can do is you can use one of the pre-trained models, and you say, well, it's all right, it's doing okay, but it's missing some stuff, or it's getting a few bits wrong. And what you can do is use that pre-trained model as your starting point, and then add to that training. And that's known as transfer learning. Transfer learning is really important because what you don't want to do, so what you can do in theory, you can create your own SpaCy model. Say, well, I don't want to use one of the pre-trained models. I will train one myself, and it will be trained on my data. Now you can do that, but be warned, it takes a lot of training, and you'll need a lot of examples if you're going to do that. Ideally, thousands. And in order to do that, you're going to have to get all the data in the right format. You're going to have to give it the correct answers so that it can train properly. There's a big undertaking. So and actually a lot of what you'll be then training is on stuff that is in every piece of text. All that stuff around picking up cardinal numbers and ordinal numbers and dates and all that kind of stuff. Well, you don't have to retrain it on that, because that's going to be in all text. So using a pre-trained model as the starting point means you can skip all that. It's already got the basics, but then you can just add to it. This is the beauty of transfer learning. You just say, well, I'll use that as my starting point, but then I'll add to that training with examples where it's struggling or which are a bit more specific to my problem area. Again, though, you do need a decent subset of examples to get a meaningful improvement. And by I mean, at least a few hundred probably examples of what you want. So it's not trivial to do it. It's also not trivial to update the SpaCy training. They've changed the process now, but it used to be you had to sort of open up a pipeline and then put it into all this sort of weird formats. But if you want to do it, there is a tutorial here that will guide you through the process, but just be warned, it's not trivial to do it. It's perfectly doable, but just be aware it's not it's not a couple lines of code and you're done. So just be aware of that, but it can help. But the most important thing to be aware of is you're going to need a lot of examples to make a meaningful improvement. So you need to bear that in mind. But your first protocol, I think, is to try different models and see how they compare. And if you've got something that's using a lot of very technical language, see if there's something very specific to that. If you're on Twitter and you're looking at tweets, use something that's been trained on Twitter as your pre-trained model. Okay, so those are the kind of basics of SpaCy for named entity recognition. Now I'm just going to show you as well another little nice little package that you can use, which actually works quite nicely in conjunction with something like SpaCy in any natural language you're doing, actually, to try and get a better understanding of your data. So we often say that when you're doing any modeling, really, the first thing you should do is have you look at your data. So when we did the machine learning stuff last week, first thing we said was have a look at the Titanic data, have a look at the stroke data first. Just see, as a human being, have a look at it and see what it looks like. The same is true with natural language processing. It's still a modeling task, and so you tend to want to have a look at the data that you're trying to look at first, to get a sense, get a feel for it. And one nice way to do that is to visualize your data, your text data, in the form of word clouds, which you've probably all seen and possibly even used at some point, where we can indicate the frequency of various words within a piece of text in a nice visual form where more frequent words become larger. And so we can get a very nice at a glance visualization of what people are saying within a piece of text. And we can use in Python, there's a really nice package called WordCloud, which allows us to generate word clouds really easily. And hopefully you all pip installed that too. So we're going to have a look at using the WordCloud package to do that, to generate a word cloud. And I've got a little example file that's based on a random review from the Internet Movie Database. Before we do that, though, I'm just going to talk you through a few key natural language processing concepts that we haven't covered yet, but which will come up in this word cloud example. The first of those is something like stop words. So for a lot of natural language processing tasks, although not for named entity recognition, usually, I'll come back to that. But when you're doing things like sentiment analysis, or as we are here, generating some word clouds, usually you're not particularly interested in the kinds of common words that are used all the time. Things like and your, the, because. Those are words that are used in all text, and it doesn't really give us anything. If we're trying to analyze the sentiment of a piece of text, that doesn't really help us much, because they're just common words that are used all the time. Similarly, in a word cloud, we don't really want to know that, we don't want to see a word cloud and the biggest words are the and. That's not particularly interesting. We're not worried about those common words. We're looking at everything in between. So usually what we want to do for a lot of natural language processing tasks is to get rid of these words. And in natural language processing, we call these words stop words. Okay. So for this that we're doing this afternoon, generating a word cloud, we're going to remove these words because they're not of interest to us. We don't want them in our word cloud. We'll do the same when we come on to sentiment analysis next week as well. There are actually pre-built lists of stop words that we can just import and say, don't give us those. And it's really easy for us to just say, those are the stop words we're not interested in. And we can also add our own as well really easily. We can say we also don't want those words too. Another concept that is very common in natural language processing is the concept of tokenization. So typically when we're doing natural language processing tasks, we usually want to break our text down basically into smaller subcomponents. Usually that's individual words, but it doesn't have to be. Sometimes it can be you break it down into sentences, or even smaller than words. You could go things like morphemes or even characters, and you can put them in a sequence like a list. So that's what tokenization is basically in natural language processing. You break down a piece of text into individual tokens. Usually that's individual words, but it doesn't have to be. And you then have a list of those words that you can work with. So each of the elements within that list after tokenization would be referred to as the tokens. So if we took the sentence dance teaching was viewed by everyone as first class, If we apply tokenization to that and tokenized by default down into words, that will be the default. Then what we'd end up with is a list of tokens, and it would break down. So the first token would be Dan's, second token would be teaching, the third token would be was, etc. Note the punctuation will remain as part of the token. So any punctuation within that word or before or after anything is attached to those string of characters will form part of the token. Okay, and that's quite important. We'll see next week how we deal with that when we don't want those things in there. We're also going to use something this afternoon called a translation table in Python. So the Python has a string class, which has really useful, I think we used it earlier in the course, has got really useful string-based methods for dealing with strings, and obviously a few of those come in handy when we're doing natural language processing. One of those methods is one called make_trans, which basically allows you to create a mapping table so that you can map one character to another in text. Say whenever you see this character, make it this character. Okay, and that could be really useful. Now there's different ways in which you can use this. We're actually going to use the third way for very specific purposes, but I thought I'd explain the others as well, because you might use these for other purposes. So if you call, let's imagine we've got a string and we call a make_trans on that string, and we just pass in one argument, then one input, then it must be the input that we pass in must be a dictionary where each key value pair, remember a dictionary is a set of key value pairs. Key is the thing we look up and the value is the associated value. Each key value pair is the key represents, here's the character you're looking for, and then the value is, and this is what I want it turned into. So here, this translation dictionary would turn all of the A's in the text into ones and all of the exclamation marks into commas. Okay. If you pass in two arguments to make_trans, then rather than a dictionary, it has to be two strings of equal length, where the ith character of the first string is mapped to the ith character of the second string. So here it's going to do exactly the same as what we did above, but in a slightly different way. So here I'm going to pass in two arguments, two inputs, as two strings. And this basically says, turn A's into ones and turn exclamation marks into commas. So whatever the first element is here, it'll turn into the first element here. Any second, whatever's in the second element here, any characters like that, it'll turn into characters like this. So they can be quite useful if you want to do essentially a sort of find and replace on your text. We're not going to use this for the word clouds. What we are going to use is this third variant here, which is where you can optionally pass in three arguments to this make_trans function. So if you pass in three inputs, it works like this second example above. But in the third input, every character that is in that string that you pass in as a third input is removed. Okay, so this variant of make_trans will say turn A's into ones and exclamation marks into commas. And also, wherever you've got a hashtag there, get rid of it. So it'll just remove those characters entirely. And if I put more characters in there, it would remove those characters too. So we're going to use a little variant of that in this afternoon's example. We also need to understand something before we move on, in that in natural language processing, indeed in any Python string, the case of a piece of text matters. So the string cheese with a capital C and the string cheese with a lowercase c, and indeed the string cheese with a capital E in the middle and a capital S in the middle, they are treated as different strings. They are not the same thing. Okay, Python will see those differently. That is, remember, a string is just essentially a sequence of characters. this sequence of characters is different because this one's got a capital C at the start, whereas this one's got a lowercase c. They are different characters. Therefore, they are different strings. Now, this is really important in natural language processing because, of course, you will be reading in text data, and the words that you're going to be looking at, people might have had them at the start of a sentence, in which case hopefully it will have an uppercase starting letter, or they may have just used lowercase throughout, or there may be typos. They've got uppercases where there shouldn't be uppercases and lowercases where there shouldn't be. For the purposes of natural language processing, generally, we don't care, particularly for stuff like sentiment analysis and also for generating word clouds. I don't care if somebody's written cheese with a capital letter or cheese with a lowercase. Cheese is cheese for sentiment analysis. That's an odd quote. And the same for word clouds. Okay, we don't want to treat these things separately. Somebody said the word cheese. So typically what we do is we just convert everything to lowercase, and that just gets rid of the problem. Just make everything lowercase, and then we'd have to worry about whether people have put capital letters in places where they shouldn't, or even where they should, and that's slightly different. That means there's no longer any difference. So all of these strings here would be converted to this lowercase cheese. Okay, so with those things borne in mind, let's have a look at the WordCloud demo. So I'm going to talk you through it now, and we're going to cover some of the things I just talked about around tokenization and stop words, and the translation table, and making everything lowercase. So we'll have a look at the text first that we're going to generate the word cloud from. Now, remember I said this is just a random review that I took from IMDb, and it was actually from the it is from IMDb. It's from the training data you're going to be using next week, but a random review from IMDb. So let's bring that up first of all. You should have that. There we go. Word cloud example text. So here you can see that this is the original review, and it's just been copied and pasted into a text file. Okay, so it's just a review from IMDb. So let me bring up, and you can see it here as well. Let me bring up the code that we are going to use. So I'm going to close down that server, and I'm also going to restart the kernel. So I'm going to flush out my variables for in a moment. Okay, so the first thing we're going to do is we need to import the stuff we need from WordCloud. So in this case, I'm going to import a word cloud because we're going to use one of those things, and I'm going to import stop words. That's the set that's been set up that has these sets of these stop words, these common words that we're not going to want to use. I'm also going to import the string library, because that's got some the translation table that we're going to be using, and I'm also going to import matplotlib, because I'm going to use the matplotlib interface to draw the word cloud. Okay, so the first thing I'm going to do, I'm going to read in the text from which I want to generate my word cloud. So in this case, that's the I've called it word cloud example text.txt. That's the random review from IMDb in that text file. So I'm going to read that in read-only mode, and I'm just going to read in the whole thing as it is. Okay, so I'm going to store it in a single string called full text. Then I'm going to grab the set of stop words that I imported. Conventionally, what we do is we take a copy of it, so that if we want to add our own, because it might be there are additional words that we also are common to our text that we want to include in the stop words, but we don't probably want to interfere with the original stop word set. Now, stop words has to be stored as a set, so I basically just create a copy that I've called stop words in lowercase, not particularly imaginative, and I just cast the original one as a set. That creates a separate copy. So we're not working with the original set of stop words, we're working with a copy. Now for this, we're not going to add anything to it, but it's good practice to do that. So I've read in my text, I've got a set of stop words that I've taken a copy of, and then I'm going to tokenize my text. And if I don't specify anything, it'll tokenize them into individual words. including any punctuation. And so all I need to do there is to use the dot split method on the string. Remember, we've read in the string of text from our text file. That's now stored in full text. If I call the split method on that, it'll break it down into the individual words, and there will be our tokens. So let me I'm just going to run these first commands first of all. So I'll highlight that, push F9, and if I do that, we can see first of all, if I look at the full text, open that up, that's read in as a single string, much as we had before, the text from the text file, that review. Then if I have a look at the stop words, this is the copy that we've taken. You can see in this set of stop words, these are the common words that we're going to tell it not to bother with. So these won't feature in our word cloud. So her, there, mustn't, were, down, with, your, ever, so, whom. There's loads of them in here. So all of that kind of stuff, that's all going to be ignored. We're not going to use those. Those are our stop words. And then we've tokenized the text. So if I have a look at tokens, you can see it's a list of length 516. There's 516 tokens in here. And if we have a look at that, we can see it's broken it down into individual words, but it's kept any punctuation within or connected to that particular word. And so we can see that here. But it's broken it down into individual words here, albeit with punctuation. Okay. Next, what we're going to do is we need to get rid of that punctuation because that's not going to help us here either. And we want to get rid of those things. Here's where we're going to use that translation table. So, and we're going to use that third variant of the make trans method, where if we pass in 3 arguments, the third argument, the string that we pass in as the third argument, is all those characters will be removed. Okay, so I'm going to set up a mapping table that does that, uses the translation table to get rid of punctuation. And we can use the punctuation, string.punctuation has stored all of the common punctuation marks that are used in text. In fact, if you type in, assuming you've imported string, which I have because I've run that first bit of code, string.punctuation, you'll see here are all your punctuation marks. This is what it will we want to remove. Exclamation marks, dollar signs, all that kind of stuff. Okay. So that is the set of punctuation stored in the string library. So what I'm going to do, I'm going to use the make trans method, and I'm going to use this 3 argument format of the make trans method. Now, the first 2, remember, are the 2 strings of text that it'll change the ith character here into the ith character here. Well, I don't need to do that for this. So I'm just going to pass in for the first 2 inputs, 2 empty strings. In other words, don't change anything from here into anything from here. Just ignore that. We're just using it to get to this third input here. And in this third input, this is the stuff, these are all the characters it's going to remove. And in this case, we want it to remove all punctuation. So I'm just going to pass in string.punctuation, which we can see is a string consisting of all of the punctuation marks. So therefore, this translation table will then remove from our text any characters in this string. So that will set up the translation table, which I've called a punctuation mapping table. And then I need to apply it. So that sets up the table that can be used, but then we need to apply that translation to make it happen. And so the way we're going to do that here is we're going to call the translate method on each token. Remember, our text is now stored in tokens. And into the translate method, we're going to pass the translation table, the one we've just set up here. So the punctuation mapping table. So I'm going to say token.translate using this punctuation mapping table for each token in tokens. So every word in every token in our list, it's going to go through and basically strip out the punctuation if there is any. Let's try that. Let's just run those 2 bits of code. Push F9. So tokens, remember, if we have a look at the original tokens, we can see we've got punctuation marks in there. But if I look at the token stripped punctuation, after we've translated it, you can see the punctuation marks have gone. So now we've got a list of tokens that are just letter characters and number characters and not punctuation marks. Now, the next thing we need to do, we need to turn everything lowercase. So what we're going to do here is we can use the dot lower method of a string to basically tell it to cast it in lowercase. There's a dot upper if you want to do the opposite, but convention says that you just put everything lowercase. That's how we tend to do it. And so again, I'm just going to use a list comprehension here. I'm going to say for every token in my tokens that have been stripped to punctuation, give me the same token but in lowercase. And that we'll put this in a list called lower tokens. So if I run that line of code, we've now got a new list called lower tokens. And if we have a look at that, we've now got a list of words that have been stripped of punctuation and have all been turned into lowercase. Once we've done that, we need to put, for the word cloud thing to work, we need to join everything back together into a single string of text. Here we're going to use the join method of a string object, which basically just tells it you pass in a list of strings and it'll bung them all together, and you can tell it how to join them. So here I'm just going to join them with a space, which is how WordCloud likes it. So you can use this method if you want to comma separate things. You can put in a comma there, and it'll give you a string that's comma separated. But here we're just going to use a space. So basically what this is saying is, give me the string which consists of an empty space character, and use that to join together all of my lowercase tokens. Store that in a single string called join string. So if I run that line of code and have a look at join string, you can see we're back to a single string now, and it's all been converted. So we've got I cannot stand different, blah blah blah, no punctuation whatsoever. There's no uppercase characters, and it's all in exactly the format we're going to need it. So once we've done all that, we can now generate our word cloud. And it's actually pretty easy to do that. So we create a word cloud object. Remember, we imported at the top, we imported from WordCloud the WordCloud object, the WordCloud class, sorry. We're going to create an instance of that. And the things we need to pass in are the size of the word cloud. This is in pixels. So the size of the word cloud that's going to be generated. The background color for the word cloud, which I think the default is white anyway, but I've specified it here. You can change that. The stop words, which remember we set up above, these are the words that it will not include. So I've just stop words equals stop words. So it's the set of stop words that I took a copy of. And the minimum font size. Now, minimum font size got interesting in WordCloud because it's not just about how it looks. The minimum font size is used as a proxy to decide which words make the cut for the word cloud. So the way in which you specify the font size will determine which words make it onto the word cloud and which ones don't. So the lower your font size, as you decrease your font size, essentially you're letting more uncommon words, rarer words, onto the word cloud. The higher the font size, you're only seeing the most common words. So you use that to kind of play around and see what how things look. So the size that we specify, the size of the word cloud, background color, the stop words, if any, that we want to use, which you almost certainly would for a word cloud, and the minimum font size. And then I'm going to call the generate method on this word cloud that will generate a word cloud of this specification, and I pass in as the input to the generate method the string from which I want it to generate a word cloud, which is that thing I created up here, which is, remember, the review text we read in that we then broke up and took out all the punctuation and made everything lowercase, bunged it back together with spaces, and then now we're passing it into the word cloud. So that will create the word cloud. Then all we need to do is plot it, draw it on the screen. So to do that, we're going to use matplotlib. We set up the figure size for the plot. We're going to turn the axes off because matplotlib obviously will by default have an X and a Y axis. We don't want that on a word cloud. We don't want any axes at all. So you can actually turn it off using this plt.axis and then pass in the string off. Will turn off axes in your graphs. You may, depending on the plots you're doing in matplotlib, sometimes that might be useful for other stuff as well. But certainly for a word cloud, you want that turned off. And then we use plot.in_show and pass in the word cloud, and that will draw the word cloud on the screen. And I'm also going to save it using the savefig method as a PNG, so we can access it after. So let's run the code, see what happens. Just give it a second to do its thing. Right, there we go. So it's now rendered the figure. So if I go into plots, we can see it's generated a word cloud. I'll open this up because it'll have saved it as a PNG as well, and we can look at it a bit more clearly here. So if I bring that up here, this is the word cloud that's been generated. So we can see that the more common words are far more prominent, and then we've got as words become less common, then they become smaller. So we can see at a glance some of the keywords that are being used in our word cloud, and I can play around with that. So I can, if I go back into my code, if I changed this minimum font size to 10, if I run that again, let's give it a second to do its thing. Now we should see that there are more words on the word cloud now, and indeed there are, and the rarer words are now being included. So if we have a look at this, we can see that's the case. Similarly, if we went in the opposite direction, I change that to a 30, and that again. Is it me? Has that not done anything? Does that look exactly the same? It's kind of done the opposite, isn't it? Oh no, that is definitely different. Okay. Anyway, have a play with that. That used to work a bit differently. Maybe they've changed that. But anyway, you get the idea. It brings up a word cloud of your specification. You can change the background color, so put blue if I wanted to. Assuming this still works. Have a look. Yep, there you go. Not particularly pleasant there, but you can have any color you want. But it's quite a nice way to be able to very easily generate a word cloud. Okay. So let's give you a go at using what you've learned this afternoon in terms of both the named entity recognition in SpaCy and word clouds. I want you to go into groups, have a go at this group exercise. So you've been provided with a file called exercise2 article.txt, which is this one here. This is actually based, this is taken from a news story that was on our, I don't know if it still is on our website, but certainly was on our website about a piece of work that Sean and Kerry did some years ago, working with one of our HSMA alumni at Devon Partnership Trust. Now, that's a genuine news story that was up there, and what I want you to do in your groups, I want you to use everything I've shown you this afternoon in terms of named entity recognition using SpaCy and the word cloud stuff that I've shown you as well, to generate some insights about this text, this piece of text, this news story. You should also explore a bit and refine your approach as you go. So you've had a look at how you get out, for example, certain named entities. Sorry, you've had a look at how you get out the labels for the named entities, the classifications. Well, maybe you're not interested in some of them. So think about how you would set up a list of those entities that are only of the type that you're interested in. Are there certain types of words that are being commonly classified as a particular named entity that might be useful to know? what are some of the most common names, common named entities that are being used? What are some of the most common words, other than your sort of the stop word common words, that are being used? Can you try and optimize your WordCloud display and your SpaCy visualizations to be insightful but clear? Now, I'm going to give you a little bit, you won't need quite an hour, so I'll give you about 45-50 minutes. We'll come back about 20 past, and I'll ask a few of the groups to show us what they've done and any insights that they found from that. So you're looking at what are the named entities that are coming out of this, and what are the sort of common words, and have a play with both of those things. If you're not, are we really going to be interested in some of the named entity types, in which case exclude them? Okay. Imagine you're presenting this information to someone that's gone and asked you to tell us something, you know, sort of interesting about this news story in terms of the text, and using your new natural language processing skills to do so. So have a play around, see what you can do. If you're ambitious, you might be able to even try it with a different model, although you hopefully should find that the general model works well. Might be worth, though, if you've got the download capacity to download either the medium or the large, but beware the files are a bit larger to do that. But you could try that as well. Okay, let me open up the breakout rooms and have a go. So get somebody in your each group sharing the screen and have a play around with it.
This meeting is...
Hi everyone. Okay, so I thought I'd bring you back now, just so we've got a bit of time, just so you can share what you've been doing. I managed to get around a few of the groups, and I was really impressed with some of the stuff that I saw. So I'm going to ask a few of the groups just to share what they did, what they were playing around with. I'm going to pick on one group in particular, first of all, because I was so impressed with their word clouds that I think everybody needs to see this. So can somebody from ZX Spectrum show us what you did, because I loved the look of your word clouds and the stuff you were doing with that.
I can. I will have to give 10 seconds for everything to run again, because the server crashed it because it wouldn't stop.
Right. No worries. It's fine.
Should be fine. So yeah, our word clouds, I think, so I was playing around a little bit with basically adding masks to the word cloud, and putting them out into different logos. So started with the basic one, which just comes up generally, and then played around a little bit with the NHS logo, to add kind of some of the words from the sentiment analysis in there, along with some of the looking at the stop words and adding and removing, which was slightly more painful than probably is necessary. But yeah, kind of most of what our digging in was around the word clouds rather than necessarily the sentiment analysis. I'm not sure it was easy to pull out much insight from that, from what we saw, but from the word clouds, it's kind of becomes easier to see what the actual article was about. So bits and pieces kind of on it's a patient and service kind of, or the article focuses on patients and the service, with added bits of mental health being a big factor. And kind of a fair bit of HSMA. We tried to remove the individual's names, so that's what we did with the stop words, just because it wasn't as hugely relevant and it was kind of showing up. So we just kind of went to see if we could do that as well, which worked, but as I said before, required a bit of fiddling.
They're fantastic. They're really, really nice. I see a couple of people suggested sharing code. Yeah, absolutely. Please do share that code in one of the public chats. It's really, really nice how you've done that. And yeah, I like the way that you sort of thought a little bit about. Sorry, I'm really I've turned monochrome. But it's how you've kind of thought about how the some of your the insight into what was basically coming out, and you know, replacing the names and things like that. That's yeah, really, really nice. And yeah, such a I saw that NHS thing. I thought that's such a lovely example of using WordCloud, and you know, so few lines of code to generate something like that. I think that's really nice and interesting how you've rather than just use the kind of frequencies, how you've based it on the named entities rather than just the raw words as well, which I think that's really nice.
Yeah, happy to share the code. Yeah, thanks.
Fantastic. Yeah, no problem at all. Okay, so I'm going to pick on another couple of groups as well. So I did say from Commodore 64, did you manage to get your sort of string replacements working? You were having a few issues with that, but do you want to share what you were looking at? 'Cause you had some quite interesting insights, I think.
Yeah, I mean, we were struggling a bit, to be honest, but I can show you as far as we got. We did get the string replace working, yeah. Right, hang on, my brain's gone. Yeah, here we go. Right, so this is the WordCloud's gone. Hang on a minute, let me bring it up again. Yeah, so we I mean, we only fixed a couple of minor problems with the data, really. One of them was that there was Devon Partnership Trust and DPT in the data, so we managed to replace all instances of it with DPT, which helped a bit. And the other thing is that there was the word S in it, which was very confusing for a while, and I thought it might be the programming language S, but then I figured out that it must be the apostrophe. So we just manually pulled out the word, we added something to the stop word list. Basically, we added S to the stop word list, and that came out. And I think that's as far as we got. I don't think we really did anything else. We did learn a bit of Python, though.
That's good. That's absolutely. It's really nice that you just thought about, sort of you could see that was a interesting insight that you had essentially, and you will have stuff like that, particularly in news articles where it gives you you commonly use the abbreviation, but also the first time it uses it, it obviously gives the full name of the organization and may then repeat that full name at various points, particularly in an article. So you end up with both. And of course, that there's things you can do to get unique instances. You're not counting the same thing twice, but obviously where you've got different strings made up of different characters, then it's interesting how you then sort of get around that. So I did post a little link as well for the rest of the group to see how you can use that method, the string.replace to map one string to another. So kind of find and replace in Python.
Now I think about it, we should have replaced DPT with Devon Partnerships, wouldn't we? Because then people looking at the WordCloud would know what it meant. But
yes, that's a good point. Yeah.
We didn't think of that at the time.
Yeah, good point. No, that's really good though. Fantastic, thank you. Okay, so before I pick on any other volunteers, which I will quite happily, is there anybody that would like to volunteer themselves before they are forcibly volunteered? Silence. I may have to get the wheel out. Okay, I'll pick on a group around. I'm not going to get the wheel out. I will just look on the list at random. BBC Micro, did you manage to get anything interesting out of the?
Yeah, so I did just put my hand up. Obviously, that wasn't spotted.
Oh, sorry, so, I can't see.
Let me share my screen. So we mainly concentrated on trying to get. Can you see? Okay, yeah, what screen am I showing?
So I've got the Jupyter notebook on.
Okay, that's good. It's not showing for me, then it's showing that screen. So we spent quite a bit of time trying to get rid of the names from our WordCloud. And so Yasser came up with this bit of code. So we were using the large whatever it is. It's late. I'm no longer able to function or say words. We added some extra stop words because there was lots of just random letters in there, and so our WordCloud we made look like this.
Fantastic. No, really nice. I liked how did you using the large model, did you notice any kind of improvement in that over the normal model?
Yes, yeah, definitely.
Good. Okay, that's interesting then. So yeah, so that just goes to show that there's kind of a trade-off you have to make with these things about whether you use the kind of the big bulkier model, which might be overkill for what you need, but on the other hand, the small model may not be capturing enough. And obviously it depends what you're trying to extract. So in reality, you're not likely going to be set a task where you say, okay, we've got this free text data, give me every type of named entity out of that. What you're probably going to have in the real world is stuff like, okay, I need to grab out the names of, so to give you an example of a project that we were going to do a few years ago with Devon Ambulance, they wanted to look at their crew notes to grab out the names of procedures that have been done. And so there, you're not interested in people or anything like that. You're only interested in one category. And so you can just filter down on that and then see how well it's picking up on those particular things. Is it misclassifying them? Is it missing them entirely? And try and adjust your model accordingly. So you know, in reality, you're not going to just be set a task where you're wanting to extract everything. So it depends on what you want to do, how you might approach something like this. But hopefully what today's showing is you can very easily, actually, using SpaCy, grab out some stuff. And certainly if you're finding that the learning isn't working too well, try one of the other models, either one of the larger core models, or if it's a very sort of text that is heavy in technical language from a particular domain, you might want to try one of the domain specific ones. Try different things, see what works best for your particular text that you're looking at, but have a play around with it, because it's a really nice piece of software, SpaCy, and there's lots of other stuff that it can do, as I say, in terms of the it doesn't do sentiment analysis. We will do that separately next week using TensorFlow, but it does do a lot of other wonderful stuff. But the named entity recognition in particular, you may find useful for your projects. It may even be that you need to you want to do a machine learning project and you want to grab out some extra information from free text fields, and named entity recognition may help you do that too. So it's good. It's a good little tool to have in your arsenal, I think. Okay, we will stop there. So thank you all for today. Hope you enjoyed it, the introduction to the world of natural language processing. Next week, as I say, we will in the morning we will look at sentiment analysis, which will I'm afraid we will be using TensorFlow again, but it will be, again, we will guide you through it, and it'll be very similar to what you did last time, except there will be some key differences in terms of the how we turn text into numbers, which is the key difference, really. But you'll see how sentiment analysis can be really powerful. You can get really good performance out of these neural network models for that kind of stuff. So you have a play with that. And then in the afternoon next week, we're going to start our journey through the behavioral modeling module, and we're going to look at cellular automata as a kind of preface to looking at some of the agent-based simulation work the following week. Also a reminder on I think it's Wednesday, I'm just double checking, we've got Tom's showcase talk. Let me just check, is it tomorrow? Yes, it is. So it's Tuesday, isn't it? Yeah, so tomorrow at 1, if you can join us, half an hour showcase talk from my colleague Tom Monks, who will be talking about some work that he and Mike did at the start of the pandemic, looking at patient transport for dialysis patients, which obviously was particularly problematic. So some fantastic work that he did that we'll be talking through, and again, another inspiration. I promise I will remember to record this one. Apologies, I forgot on the last one. Okay, thanks everyone. Have a play around, and I will see you next week. Bye everyone.
Thanks, Dan.
Thanks, Dan.
Cheers all. Thank you.
Thanks.